Recording in progress. Recording stopped. Recording in progress.
Everyone. Mas Adi, can we start or can we start?
Yes, there is. We wait to Dr. Sanjay.
Oh, waiting for him.
Yes, because there is no Dr. Benoit here.
Dr. Ben is sick. He's getting sick, isn't it?
Yes. The latest news is.
And she already sent us the video or presentation or not?
There is no.
He will go join us.
No, yeah, Dr. Benoit. No, there is no video for Dr. Benoit, so we cancel with Dr. Benoit. So we can go into Dr. Sanjay.
Okay, so I think for Dr. Sanjay.
Yes.
Okay.
Oke, Dr. Jamal. I
Yeah.
think Dr. Sanjay is already joined with us.
Oh,
Yes.
Thank you. So maybe we can start, Dr. Jamal.
yes. Okay.
Okay. Okay, thank you. I will share the short bio of our invited speaker.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. My name is Jamil Malik. You can call me Jamal. Your moderator for today, and with great pleasure, I welcome you to parallel session 4 that focusing on biomass processing. Right? We have actually initially two invited speaker, but one and namely Dr. Ben is getting sick, right? So she couldn't come or join with us today. But we will come to Dr. Sanjay as the invited speaker today. And also we have 15 presenters. Well, so much. But before we start this session, I would like to remind you that we would love to deliver an interactive session between you and the speakers. Therefore, for the presenter, we invite you to turn your camera on once we start introducing you, playing your video present, and beginning the Q&A session. For the participation, we also welcome you to do so. However, if you are not available to turn your camera on, you may use the raise hand button or your screen to deliver your question, as we will turn off the chat room once we start the Q&A session. For the best audio quality, we recommend you to use any listening devices, and since this is an online forum, you should may enjoy the session together with your colleagues at work or family at home. The second ICONLIG 2022 can also be accessed through our official YouTube channel. So you also may stream it live from your phone, portable computer, tablet, and laptop. So we turn to the first session as invited speaker, namely Dr. Sanjay, already here. Hello, Dr. Sanjay. Dr. Sanjay.
Yeah.
Oh, okay. Thank you.
Yes.
So,
Hello, everyone.
yeah.
Hello.
First of all, I will introduce your. I got your short bio. Dr. Sanjay Manfin Rangapais, right? Is currently working as a senior research scientist or associate professor, and also advisor within the Office of the President for University Promotion and Development toward International Goals at King's Mongkut University, right? Of Negeri North Bangkok, Thailand. He received the PhD from Faculty of Mechanical Engineering Science from Visvesvaraya Technology University, India in 2018. And I read your short bio, so many achievements you have. So I appreciate for this great achievement. So I think it's better to directly hear the directly presentation from Dr. Sanjay. And if the all participants have any question, we'll provide the time in the after this session. Thank you. I think we can start presentation. Yes, Dr. Sanjay.
Please can go with my presentation. Yes, video presentation.
Okay, we can start now, Dr. Sanjay. Okay.
Good morning to everyone. Myself, Dr. Sanjay. I'm a senior research scientist and associate professor and also an advisor within the Office of President for University Promotion and Development towards International Goals at King Makur's University of Technology, North Bangkok, KMTV, Thailand. Before my presentation, I would like to thank all committee members for kind invitation. My presentation topic is lignocellulosic fiber reinforced composites, progress, performance, and application. As we know that if natural fibers as a reinforcement materials in composites, then we can call them natural fiber composites. And natural fibers are nothing but the fibers which are derived from natural resources like plants, animals, or some other living species. For an example, jute, canop, sisal, bamboo, banana, etc. are natural fibers that are extracted from plants. On the other hand, wool from animals, feather from birds, these are all some natural fibers. Now, I am going to present general highlights of natural fiber composites. As we know that recently, the environmental impact of synthetic fibers has inspired scientists to focus on using natural fiber as a reinforcement material in polymer matrices. The recent extensive studies and development efforts has directed that natural fibers, as I mentioned earlier, such as jute, sisal, canop, bamboo, banana, etc., can replace synthetic fibers like glass fibers and carbon fibers. Most important, the natural fibers are abundantly available resources in all countries, which are cheap and easily renewable and even biodegradable. Another important highlight is natural fiber reinforced composites are reasonably strong, lightweight, and biodegradable. Hence, they have the potential to be used in several applications. Also, the use of natural fiber composites in industries has steadily increased. Recently, it is steadily increased, benefiting fiber plant production and world's economy, which means it will be indirectly helpful for our farmers and agriculture. So, recent developments in natural fiber composite studies have illustrated the great potential as structural components in various applications. See this figure. It has represented the number of publications based on materials composed of natural plant fibers between 1997 to 2019, found in Science Direct using the keyword natural plant fiber composite. And each year there has been a steady increase in the number of published work. So that means natural fiber composites is one of the notable research area for development of eco-friendly materials. This slide presents factors which are affecting the performance of natural fiber composites. This slide especially for upcoming researchers. See, based on these factors and parameters, the upcoming researchers can identify new research works on natural fiber composites to develop sustainable and eco-friendly materials. The first factor is selection of natural fibers based on the parameters such as type of fiber based on its origin. That means the fiber derived from plant fibers, as I mentioned before, such as canop, jute, sisal, etc. are comes under plant fibers. Animal fibers such as wool, hair, feathers from birds, or mineral fibers like basalt fibers. Even geographical locations based on environmental conditions, harvesting time, chemical composition. That means chemical composition of natural fibers such as cellulose, hemicellulose, lignin, extraction method, chemical treatment and fiber content, surface topology, fiber size, fiber length. Even we can do the new research based on the properties of natural fibers such as density, hardness, thermal properties, modulus, strength, elongation at break, etc. Fiber dispersion in composites depends on bonding between fiber and matrix. As we know that fibers are hydrophilic in nature, and that means natural fibers are hydrophilic in nature and matrix is hydrophobic in nature. So chemical modification is the only solution to reduce the hydrophilic nature of natural fibers. That means that will be helpful to increase the bonding efficiency between fiber and matrix in composites. Even we can also do the work on orientation of fiber to improve the properties of natural fiber composites. Other factors such as matrix selection like thermoset, thermoplastics, biopolymers, composite interfacing properties, also consider for even composite interfacing properties also considered for improvement of performance of natural fibers. We can also do the work on composite processing method and composite characteristics. Now I'm going to explain performance and durability aspects of natural fiber composites by using noteworthy results of my own publications. And this research study, the extraction and characterization of waste fibers from water icing plants, and also the fabrication of bioepoxy based eco-friendly composites from chemically treated water icing fibers. And we know water icing is an aquatic plant collected from near Chom Prai River, Bangkok. Here in this research, the water icing fibers are chemically treated by NaCOH, means sodium hydroxide, and silane solution, and bioepoxy as a matrix material for making composites. The raw NaOH and silane treated water icing fibers reinforced bioepoxy based composites are manufactured by casting method. Then different tests were carried out on prepared composite specimens. This research, especially this research, revealed that the composites made by chemically treated fibers, either from NaOH or from silane solution, have better results when compared with raw fiber reinforced composites. This study confirmed that water icing fibers can be used as a reinforced material with bioepoxy polymer to develop fully bio-based eco-friendly composites for production of lightweight structures. This is the one. This other work, this investigation is an attempt to develop kanal sisal fiber from fabric reinforced bioepoxy hybrid composites, and we assess the performance of composite under isolated weathering conditions. The bioepoxy resin and kanal sisal fiber fabrics were used for making hybrid bio-based composites and manufactured composite laminates using compression molding method. For comparison purpose, a neat bioepoxy thermoset was fabricated by casting molding technique. To promote the accelerated weathering of composites, the samples were exposed to environmental conditions such as ultraviolet radiation, extreme temperature and humidity conditions in accelerated weather tester machine according to STM G155 13 cycle 1. The tensile, impact, morphology, TGA, DMA and water absorption test were performed for both before and after weathering test samples according to international standards. From this research, the results indicated that the manufactured fully bio-based enough sizzle fiber reinforced hybrid bioepoxy composites show moderate properties when compared to neat bioepoxy composite at both before and after weathering condition. That means reinforcement of natural fibers in polymer composite can increase the properties of composites. Also, from the result, it is worth to point out that these fully bio-based composites are promising composite material for semi-structural applications. This investigation is an attempt to assess the hybridization effects of different laminate stacking sequences involving jute enough e-glass over fabric. The composite laminates were fabricated using vacuum bagging method. This study reveals that the vacuum bagging method is a very effective method to prepare composites with low void volume fraction. The tensile properties of composite laminates were influenced by the strength and modulus of fibers. And the tensile, flexural and hardness properties of composite laminates mainly depend on the sequence of high strength fiber lies in the laminates and also influenced by stacking sequence and adhesion levels of fabrics. It is also noted that the hybrid laminate having glass plies as skin layers and natural fiber plies as a core layers showed better tensile, flexural and hardness properties. Also from SEM analysis, scanning electron microscopic analysis, it is evident that the good composite properties all depend on the presence of fewer voids and proper adhesion between fiber and matrix. This research investigation on development of composites by flask basalt carbon fiber reinforced with both bioepoxy and synthetic epoxy under different stacking sequence techniques. These composites were fabricated using a manual and layup method and compression molding technique. This investigation revealed that the hybrid laminate having basalt fiber, that means mineral fiber, or carbon plies, means synthetic fiber, as a skin layers and natural fiber plies as a core layers showed better tensile, flexural and hardness properties. From this research, it is also noted that the mineral fiber, that is basalt fiber, also viable material for replacement of carbon or any synthetic fibers. This research investigation intends to recognize the effect of laminate stacking sequence of natural fibers, e-glass, carbon fabrics, reinforced hybrid epoxy composite. Here we have used one natural fiber and two different synthetic fibers. And manual and layup method is used as a fabrication method, while studies on physical, chemical and morphological properties has been conducted in this research work. From the results obtained, it is obvious that the properties of natural fibers, e-glass, carbon fiber reinforced epoxy composites enhance due to the hybridation with that means the properties of composite will be increased by addition of either e-glass or carbon fabrics in natural fibers. This work based on performance of hybrid composites improved by using different natural fibers and adding particulate fillers to them. In this study, we studied the mechanical and tribological properties of jute, sisal, e-glass fabrics reinforcing matrix reinforced with a matrix such as natural rubber and synthetic epoxy and filled with different proportion of tungsten carbide powder WC powder. Results revealed that there is a significant change in the mechanical properties and enhancement of wear behavior was noticed due to the incorporation of filler particles. That means filler loading can increase the mechanical properties and decrease the wear rate by increasing the bonding property between fiber and matrix. And this investigation was performed to study the effect of titanium carbide (TiC) nanoparticles and coir fiber as hybrid reinforcements on physical, mechanical, and thermal stability of coir fiber incorporating with titanium carbide epoxy composites. This work proves that the incorporation of TiC, that means titanium carbide nanoparticles in coir fiber epoxy composite, exhibited some improvement in mechanical characteristics. Application of natural fiber reinforced composites. This figure shows some of the applications made by natural fiber composites. Hybrid composites, that means natural fiber with synthetic fiber, find their applications in automobile and automotive sectors like in the production of car interior parts, doors, headliners, decking, dashboards, pallets, spare tire covers, seat backs, spare wheel panels, etc. They also may be used in household applications such as chairs, lampshades, roofs, suitcases, tables, bath units, etc. In the marine field, they find applications in the manufacturing of boat hulls, fishing rods, etc. In the sports sector, they are being used in the manufacturing of tennis rackets, bicycle, sports helmets, etc. And they are also utilized in manufacturing of storage devices like post boxes, grain storage silos, and biogas containers. I'm requesting audience to refer my recent review articles for more information on natural fiber composites. I'm happy to say this, most of my review articles are most cited articles in top journals. And now I'm presenting observation and knowledge gaps based on my literature survey on natural fiber composites. Most of the researchers used hand layup and compression molding methods for preparation of composites. So upcoming researcher can do research on effects of various manufacturing processes. Recent researchers has been focused on the impact of stacking sequence and hybridization of synthetic fibers with two or more natural fibers to increase the properties of natural fiber composites. The hybridization of natural fiber composite by another natural fiber does not yield superior mechanical properties as compared to hybridization by synthetic fiber. And one of the most important challenges facing researchers today is to achieve a better interfacial bonding between natural fibers and polymers. But this is quite difficult due to hydrophilic nature of natural fiber and hydrophobic nature of polymers. But the chemical and surface treatment to natural fibers are a better solution to overcome this problem. Composite materials reinforced with natural fibers are best option to replace synthetic fiber composite, at least for low load applications. Researchers substantiated that the materials made from renewable sources such as natural fibers embedded in a matrix of polymers called biopolymers offer as good alternative to synthetic fiber composites. These are all my books published in Elsewhere, Sprintor, Ville, CRC+. As of now, I have published 28 books. If any kind of queries and collaborations, please contact me by email. Surely I will address those emails.
Okay, thank you, Dr. Sanja, for very interesting presentation today. So now is the Q&A session. If the represented participant have any question, please directly raise hand and deliver the question to Dr. Sanjay. Any question, please? Or you can write down in chat room.
Yes.
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 Yeah.
Hello.
Yeah.
Okay, thank you. I have a question. Maybe the next question from the other participant. Hello. Hello.
Yes, please.
Okay. Thank you very much for your impressive presentation. My name is Adi Banawan. I'm researcher from Research Center for Biomass and Bioproduct. And today I have many questions to you that you can share with us. And my first question is, what is your opinion about building component products with composite reinforcement based on? Hello?
Yeah. Please
Sorry.
continue your question.
I think your internet is not stable.
Yeah.
I'm not hearing properly. Yeah.
Okay.
I think it's a frequency problem.
You can repeat. I think
Yes.
short question, please.
Okay. What is your opinion about building component products with composite reinforcement based on fire resistant or fire retardancy and hydrophobic materials? The second one is about nano-sized fiber. Mechanically, will the nano-size strengthen the reinforcement composite? Is it my two questions? Thank you.
Okay, you were asking about the properties. Okay.
Yeah.
I think in my presentation itself, I have explained already. For using natural fibers, especially lignocellulosic fibers in polymer composites, the fibers that particularly the natural fibers are hydrophilic in nature. So if you do the chemical treatment or surface treatment, you can reduce its hydrophilic nature. That means it will be moved to hydrophobic nature. If you combine the hydrophobic nature of fibers with polymers, then we can get better natural fiber composites. And we can use it that for many applications. Recently, we have done automatic people mover inside the complete interior made by natural fiber composites. But before making composites, we have done a lot of chemical treatment and surface treatment for the natural fibers. For making products, as you asked the question, For making products, we have to take care more things about surface treatments and chemical treatments for natural fibers.
Okay. Thank you.
Question up?
It's a good question. It's a good question. Yeah.
Yeah.
Yeah. Thank you, Mr. Jamaluddin and Dr. K.
Okay, no worries. Any other question from other participant, please?
Yeah, please.
Oh, Bu Yayan, please.
Yes.
Yes.
Thank you, Pak Jamal. Hello, Dr. Sanjay. My name is Yayan. So, hello. So I see your slide about using water hyacinth as the fiber for epoxy, right? So what part of water hyacinth do you use, and what is your reason to use water hyacinth for the natural fiber in your epoxy? And how the properties, I mean, like, does it really significantly improve, or what kind of properties do you intend to improve with the incorporation of water hyacinth? Thank you.
Okay. Good question. Good question. First question, actually, what part of water hyacinth we are used? Right. Good question. Actually, we are used the fibers of natural water hyacinth, fibers which are extracted from water hyacinth, which we have used for making composites. That's the first thing. The second thing, regarding about the property, yes, we can achieve good property better than the polymers, but not equivalent to the synthetic fiber composites. Okay. So if you want to improve the properties with using water hyacinth fibers, so we can do one thing, like I have presented many things. We can use the synthetic fibers incorporating with water hyacinth plants, like outer layer or skin layer as a synthetic fibers, or inside we can use water hyacinth plant fibers. Even in the different forms, we can use water hyacinth, either in the particulate form, other in the fabrics form. Yes, in particulate and fiber, if you compare, the fiber reinforced composites will give more properties. So it all depends on how to improve the properties of natural fibers. And another thing you have asked, why you choose the water hyacinth, right? Because actually it's a best plant and it's available in Bangkok. Availability all depends on the availability of water hyacinth, which we have used for making natural fiber composites. It's like waste plant fibers to making some good products. Yes. I hope
What? Yayan,
my response
is enough?
Yeah, thank you.
Okay. Yeah. Okay, thank you, Sanjay. One more from me. It's a general question.
Please.
Yeah, it's a general question, but maybe you got the news from our country that one city in Java province, West Java province, Cianjur, hit by an earthquake 4 days ago. Many people died, or 100 people died, and then 1,000 houses damaged. In terms of your topics, which one is it? Reinforced lignocellulosic reinforced composite is reliable for our house building. Remember that Indonesia is a humid country, right? High raining and stuff.
Yeah.
So, what's your recommendation for this?
Yeah, it's a wonderful question actually. Actually, already the people are using bamboo fiber reinforced composites for making homes. That means lightweight materials for making homes. Yeah. So we can use many kind of natural fibers which are depending on the country. Like you are from Indonesia, but many natural resources are available in Indonesia. So you can use, based on the property and availability, making it reinforcement with any kind of polymers, either biopolymer or synthetic polymers. Definitely, we can make homes with lightweight homes with natural fiber composites.
Okay, Thank you, Mr.
Yes,
Dr. Sanjay.
yes.
We have limiting time, so I think we can finish our session with you.
Excuse
And
me,
again,
excuse
thank
me,
you.
Dr. Jama.
Yeah.
I think still there is one question in the chat room.
Oh, okay.
Oh, okay. The
Yeah,
question
yeah,
is
yeah.
from Professor Eros.
Yeah. How about
Okay.
the potency of nanomaterial to apply in macro composite? About properties and about the price. Please, Dr. Sanjay.
Okay. It's a really good question. And the properties of nanomaterial. Yeah, of course. I have already presented in my slides. We have used many kind of nanomaterials, even organic and inorganic nanomaterials in macrocomposites. Definitely, it will improve the mechanical properties as well as tribological properties. And another thing is about price, right? Price, it all depends on the choosing the materials, either natural fibers or matrix materials. So it all depends on the individual materials. Some natural fibers are very cheap, some natural fibers are costly. So it all depends. But of course, nanomaterials or nanoparticles in composites, definitely it will increase the properties of composites. Of course. I have many publications on nanomaterials which are reinforced with natural fiber composites.
Yep.
Yes.
Okay, this is Aheru.
Thank you.
Okay,
Dr.
yeah.
Sanjay.
So
Nice
because
to
of
meet
limiting
you.
time, Dr. Sanjay, it's interesting discussion today, but the time is limited for us. So we should finish this session. And again, we thank you for your joining with us. And we
Thank
have
you
your
for kind invitation and
certificate.
opportunity, and have a nice day. Thank you everyone. All the best.
Any certificate for Dr. Sanjay?
Hello.
Yes.
Wait a minute. Wait a second, Dr. Sanjay.
Please.
Give you one fish certificate. Yeah, you are. Again, thank you for your presentation today. Very interesting.
Thank you.
Thank you.
Everyone.
Yeah. Okay, let's move to the next session. We have 15 topics, 15 presenters today. Divided into 3 sessions. And for the first opportunity, we give to
Mr.
Pak Nur Adi and the team, yeah. The title effect of acquisition parameter on absorption properties of activated carbon prohibited from thick waste. Yeah, short bio of from Nur Adi Saputra, born in Kuningan, West Java, and obtained bachelor from UNWIM and master degree in Yunnan University, and now studying for his doctoral level in IPB University, majoring in forest product technology. She already has many achievements, and you can contact him by email as you can show in your screen. So time is yours, Pak Adi. Oh, this is the second author. Yeah, Nur Aisyah Hanifah from Agricultural Technology Universitas Pajajaran. Aisyah research focus on the biomass as well, and present collaboration with Adi in their paper. Oh, we should deliver all short all of the person or one by one.
I think we can tell the short bio of first five presenter,
okay.
Dr.
Yes, please. And then Don Pedro, and graduate from Brawijaya University. Well, I think he's expatriate, right? From Brazil or something. Fred is conducting research, this is under Dr. Lisman Negara guidance or supervising at the Laboratory of Biomass and Bioproduct BRIN from March to 2022. And then, who else? Yeah, and then Putri Amanda, she is researcher who break into interfiber in wood. Wow, just to establish again. Next, Aska Sabila Hanifah, currently is a MSc student in Islamic State University, UIN in Jakarta. Research assistant in polysaccharide engineering group from Research Center of Biomass and Bioproduct, joined in 2021. And next.
Okay, Dr. Jamal. We will play the 5 video from the presenters.
Oh, all by video, right?
Yes.
Okay. Yes. Okay. Please, Pak Adik.
Hello everyone, and welcome to the second International Conference of Lignocellulose. Today we will talk about the effect of activation parameters on adsorption properties of activated carbon prepared from thick waste. I am Adi, and I work with Jenny Hendra in this present study. So this is our content of presentation. The first one is introduction, and then experimental design, and we are talking about the result, and we will discuss it. And then the last one is conclusion. So I think in this room, everybody in this room knew the teak or jati. Teak is a species that has multi-benefits, such as for ecology, economy, construction, or furniture. So in general, the teak was contribute to the circular economy. Teak processing generate residue that may be an environmental issue. In addition to processing, the thinning system, like the silviculture system, increase the amount of residue in the environment. Pyrolysis procedures have been proposed to address this concern, and thermochemical mechanism convert residue into porous material for many applications, like for adsorbent application. Pyrolysis parameter, including temperature and contact time, affecting the quality of the prepared product. So this study intends to investigate the impact of pyrolysis parameter on adsorption behavior. So this is our experimental design. The first one, we cut off the thick log, like 10 centimeter in diameter, and then 30 centimeter in length. And we carbonize the thick log in the drum kiln for approximately 10 hours. And after that, we conditioning overnight. The next step is we reduce the particle approximately 5 millimeter. And then for the activation procedure, we use two temperature setting, like 750 and 800 degree Celsius. So for the holding time, we use some variation here, like for 50 minutes, 20, 60, 120, 180, 210, and 240 minutes. So we employ the activation agent, like We use superheated steam at 300 degrees Celsius. And for the product, we use coding to simplicity the sample. We use AC or activated carbon, and then temperature, and then contact time. And we conduct the investigation through the proximate analysis and iodine index in milligram per gram. And from the table one, we knew that the increase in temperature and holding time result in a decrease in yield, moisture, and volatile. This pathway is to expose the mineral and carbon. So for example, the highest carbon content was 90.77%. It's originate from activated carbon using 800 degrees Celsius and 240 minutes for holding time. So actually, the source of volatile derives from the decomposition of hemicellulose and cellulose, while lignin is maintained to produce carbon fraction. The improvement in product quality is attributed to the rejection of volatile. This is iodine adsorption graph. From this graph, we know that increased adsorption of iodine is associated with an increase in pyrolysis parameter. So it's like pyrolysis parameter have positive interaction with the quality of product. The active site for iodine storage are believed to be effective by temperature and holding time. And it's very ruled by temperature and holding time. So the amount of iodine absorbed represents the number and size of the resulting force, although it is not as detailed as the surface area analyzer, but the iodine absorption may detect the microporosity development. And the highest iodine absorption in this study was 187 milligram per gram. Also, we conduct the comparison study between various material. So from this, you can see from this table number 2, that the chemical activation produce a high quality of activated carbon, like from KOH, it's generate the iodine adsorption in 1,800 milligram per gram by WHO in 2022. But in other side, the physical activation pathway, like using steam or gases, are taken considering the convenience and more economical compared to chemical that require washing procedure after activation. So in my opinion, the micro, meso, and then macro pore transition was responsible for decreased porosity properties, typically in physical activation. Like the larger pores, it will reduce the iodine adsorption. So here our conclusion, the temperature and holding time may reduce yield through the volatile removal to the liquid and gaseous phase. And the further reaction between gases and solid surface provide improved microporosity. This is characterized by increased iodine adsorption. The pyrolysis parameter exposed as content, which in particular portion will block further pores development. So I think the S content could be one important point from the beginning. The iodine index detects the development of microporosity of activated carbon pair. And the present study produced the highest iodine absorption of 187 milligram per gram. Thank you for your kind attention.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Hanifa. I'm from Department of Agroindustrial Technology, Universitas Pajajaran. I'm going to talk to you about my research on production, optimization, and characterization of cellulose acetate from oil palm empty fruit bunches. I got interested in this area because we know palm oil production residual waste of oil palm empty fruit bunches has potential and opportunity to be utilized optimally, contain about 3687 to 4857, 56 cellulose, and the cellulose derivative were studied to overcome the limited solubility of cellulose in organic solvent, one of which is cellulose acetate. Cellulose acetate contains acetyl, which regulates solubility in certain solvent. The solubility of cellulose acetate can be adjusted according to the degree of substitution, and acetyl content is the amount of acetyl is directly proportional to the degree of substitution. The percentage of acetyl cellulose acetate required for commercial scale according to SNE, which is between 39 to 40%, and cellulose diacetate resulting from the hydrolysis process. This research was conducted based on various factors that influence the hydrolysis process, such as the ratio of water to cellulose, reaction time, and temperature. The cellulose acetate production process consists of 3 stages and are material preparation, cellulose extraction, and synthesis of cellulose acetate. Material preparation to remove adhering dirt and analyze for lignocellulosic content, and the cellulose extraction is extraction through several steps: hydrolysis, delignification, pulping, and bleaching. When the synthesis of cellulose acetate consists of 3 stages: activation, acetylation, and hydrolysis. In the hydrolysis process, water and cellulose were added 1:1, 2:1, and 3:1 ratio at a variation time 30, 45, and 60 minutes, and the temperature 40, 50, and 60 Celsius. Optimization is done by using response surface methodology. Thermal analysis was performing using thermography metric analyzer and a differential scanning calorimetry. The morphological analysis was done using Fourier transform infrared. After adding the result of this study, it is known that the cellulose content in oil palm empty fruit bunch had cellulose content ranging of 31.9 to 50%, and cellulose is the large. The high cellulose content in oil palm empty fruit bunch has the potential to be further utilized. And cellulose extraction is needed to be obtained pure cellulose or so-called alpha cellulose. And the stage of cellulose extraction are hydrolysis, delignification, pulping, and bleaching. The final product of the cellulose extraction process is alpha cellulose, and the alpha cellulose produced has a very high level of purity. And cellulose acetate is produced using a glacial acetic acid as a solvent and acetic anhydride as a reactant, as well as the addition of sulfuric acid as a catalyst, which is commonly used in the industry. And the stage of making cellulose acetate consists of activation, acetylation, and hydrolysis. The activation process is carried out to expand the surface of the cellulose to facilitate the formation of ester in the acetylation process, which produces cellulose diacetate. In the first step of the acetylation process, acetic anhydride pick up proton from the concentrate sulfuric acid, and a proton attached to one of the lone pair of electron in cellulose oxygen is double bond to carbon. Oxygen will acquire a positive charge due to a proton transfer, and the acetic acetic group in the acetic anhydride will be easily substituted to form a sulfoester group. And cellulose triacetate resulting from the acetylation process was then hydrolyzed in an acidic medium, and the rate of reaction as well as the rate of substitution depend on the amount of acid, temperature, and reaction time. And the resulting cellulose triacetate was partially hydrolyzed to obtain the acetic acid. The addition of water and acetic acid to cellulose triacetate react exothermically, and when the amount of water increases, the reaction takes place and complete hydrolysis occurs. The result of cellulose triacetate have a whiter and smoother color than alpha cellulose. In the study, a hydrolysis process was carried out with independent variable of process condition, water to cellulose ratio, reaction time, and temperature, to determine the optimum hydrolysis condition to obtain cellulose acetate with acetyl content that met requirement of SNE 39 to 40, and the resulting cellulose acetate contain an acetyl content of 35 to 42%. And the hydrolysis process aims to reduce the degree of substitution or acetyl content to a certain level. In the study, the cellulose diacetate to be obtained has an acetyl content 39 to 40%, and which is in accordance with SNE. Determination of the optimal point for acetyl percentage was carried out using response surface methodology and simulate 5D treatments with various combinations for future response data obtained and analyzed to obtain a mathematical equation that gets the best response. And based of the result on NOVA, it can be seen that the model has a significant influence. The lack of it test shows significant result, and it shows that the model made is in accordance with the design. It can be seen that the quadratic model of acetyl content of the cellulose diacetate obtained has a relatively high coefficient of determination. And the results show that the ratio of water to cellulose has a very significant effect. The higher ratio of water to cellulose will cause lower level of acetylene cellulose diacetate produced, and the hydrolysis reaction by adding water will stop the ongoing acetylation process. This is the goal. During hydrolysis, the acetyl group of cellulose triacetate is exchanged from the hydroxyl group of water, and cellulose triacetate has triacetyl groups, so that during the hydrolysis process, 1 to 3 acetyl group can be substituted by hydroxyl group from water, and if only one acetyl group is substituted, the resulting product has a degree of substitution of 2, also known as cellulose diacetate. The addition of water is not done directly, but in the form of water dissolved in acetic acid and added slowly, so that there will be no formation of cellulose diacetate clump. And the time factor no longer the hydrolysis process is carried out, the more substitution of acetyl group by hydroxyl group occur, and the hydrolysis temperature has a negative linear and very significant effect on the level acetyl cellulose acetate. They show that a constant ratio of water and hydrolysis time, the higher the hydrolysis temperature and the lower of the level of acetyl cellulose diacetate produced. An increase in temperature can increase the rate of the hydrolysis reaction due to the addition of kinetic energy, so that molecule can be moved faster and there are more collision between molecules. And determination of the optimum factor. The software showed that the optimal solution consists of water to cellulose ratio of 2 to 1, a reaction time of 60 minutes and a temperature 30 Celsius, which produces as predicted response of 39.5%. And model validation is carried out to determine the level of model accuracy by comparing the data predicted by the model with the actual data from the analysis. The optimal formula according to the predicted efficiency and indicate that the model is adequate for the optimization of factor of variable. And the thermographimetric analysis, commercial cellulose acetate experience have methylose less than synthetic cellulose acetate, and the methylose can be caused by the loss of volatile compound in water bound to the hydrophilic group of the cellulose acetate chain, and the drastic reduction in mass due to the thermal decomposition of the cellulose acetate polymer chain. And the differential scanning calorimetry, based on the table, it can be seen that the glass transition of temperature for synthetic cellulose acetate is higher than commercial cellulose acetate. When the outside temperature approach the glass transition temperature, the polymer will change from a hard rigid condition to a soft rubber-like state, and then the continuous increase in the temperature causes an exothermic decomposition to reach the melting temperature, and the melting temperature of synthesis cellulose acetate is higher than commercial cellulose acetate, and this is influenced by difference in raw material for cellulose acetate. As observed in figure, Fourier transfer infrared, synthetic cellulose acetate and commercial cellulose acetate have a spectrum of the hydroxyl and indicate that there are hydroxyl group in the cellulose diacetate. Carbon hydrogen bond group +1 and carbon oxygen double bond group, which can be attributed to the stretching of this carbonyl ester and is a characterization of the acetyl group, which indicated that the cellulose is acetylide. And the conclusion from my research, cellulose acetate is synthesis throughout the stage of acid activation, acetylation, and hydrolysis, and the optimization of this hydrolysis process was carried out using the ratio of water to cellulose 2 to 1 time 60 minutes and the temperature 30 Celsius, which result in cellulose acetate with an acetyl content 39.40 459%, and the thermography analysis showed that the commercial cellulose acetate lost mass 12.16% until the temperature reached 185 Celsius, and while synthetic cellulose acetate lost mass of 13% up to a temperature of 170 Celsius, and in the next stage, the mass loss reached 70 to 80% at a temperature of 100 to 400 Celsius, and drastic mass reduction due to the thermally decomposition of cellulose acetate polymer chains, and analysis of differential scanning calorimetry showed that the synthetic cellulose acetate had a glass transition higher than commercial cellulose acetate. And this is possibility influenced by the use of different raw materials from the manufacture of cellulose acetate. Morphological analysis using Fourier transfer infrared showed that the cellulose acetate consists of the hydroxyl group, carbon hydrogen bond group, and carbon oxygen double bond group, carbon oxygen bond group, and glycosidic bond. Thank you for your attention. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Good afternoon, ladies and gentlemen. Today, I would like to present our research about isolation and characterization of cellulose nanofiber from sweet sorghum with different ultrafine grinding modes. So, sorghum is a rapid-growing plant which originated from Africa that can be harvested 3 to 4 times a year. This plant is commonly used to produce starch from its seed, and it can use to produce sorghum juice for the bioethanol production. But in the juice extraction process, it leaves sorghum bagasse which have a high content of cellulose, and this bagasse is abundant, which are potential to be source of cellulose. And cellulose fiber is a polymer that can be found in plant cell walls. There is a strong hydroxyl bond in the polymer which result in good mechanical and thermal properties. Matibe and Nobuta has reported a drastic improvement in this characteristic, and due to its high specific strength modulus and reactive surface, cellulose fiber have been extensively researched and applied as a reinforced composite with a certain polymer matrix. Previous studies shows that strength of cellulose composite can exceed magnesium alloy and approach a stainless steel. And to isolate cellulose nanofiber, it can be done through either mechanical or chemical method. Previous studies showed that cellulose fiber can be isolated from sorghum using alkalization, followed by bleaching process with sodium hypochlorite. However, the current waste from this process can be harmful to the environment. So we need an alternative, such as using hydrogen peroxide and alkaline hydrogen peroxide in the bleaching process. But it still needs a further chemical analysis in the chemical treatment that we apply. And to produce nanocellulose, it can be done using chemical or either mechanical method. Yulianto have demonstrated that nanocellulose can be produced using acid hydrolysis and panels using high-pressure homogenizer. But there are some disadvantages from these methods, such as resulting chemical waste and excessive use of energy. Supian showed that ultrafine grinder can produce nanocellulose without chemical waste, more efficient use of energy, and high yield compared to other mechanical methods. However, the process of extracting cellulose nanofiber from sweet sorghum bagasse by using combination of chemical and ultrafine grinding has not been found in previous study. So the objective of this research is to isolate cellulose nanofiber from sweet sorghum bagasse using a combination of chemical and mechanical treatment. And the second is to study the effect of chemical treatment and different gaps of ultrafine grinder on the chemical and physical properties of cellulose nanofiber. So the isolation start with grinding and sieving raw sorghum bagasse to obtain a sorghum powder with a particle size of 40 mesh. Then this powder is delignified with sodium hydroxide, and the delignified pulp is bleached using a hydrogen peroxide first and bleached again with the alkaline hydrogen peroxide to get the cellulose fiber. Next, the cellulose fiber is fibrillated using ultrafine grinding with a gap variation start from 10, 30, 50, 70, 90, and the smallest is minus 110 micron. And the fibers are characterized. And these are the characterization that have been done in the study. The chemical content analysis using method by Van Soes, the morphology analysis by field emission scanning electron microscopy, functional group analysis by Fourier transform infrared spectrometer, and crystallinity analysis by X-ray diffraction. So these are the result of chemical content analysis that showed that the delignification followed by bleaching process decreased hemicellulose and lignin content and increased cellulose purity. And from this result, the cellulose that we obtain in this research can reach 69.92%, which still contain 6.69% of hemicellulose and 0.61% of lignin. This data is also supported by the FR spectrum analysis that the spectrum showed several peaks in the spectrum. The blue circle showed peaks at 3000, which indicate the presence of hydroxyl group in the cellulose fiber, and the yellow circle showed the disappearing hemicellulose fraction by the decreasing of intensity in the peak, and the red circle showed the decreasing of lignin fraction by the disappearing peak in 15013, and also the last is increasing cellulose purity by indicates the peak of 100 and 1159 and 896 that indicates the COC bond at the 1.4 glycosidic bond of cellulose, which showed that the purity of cellulose fiber was increased. So the cellulose fiber was successfully isolated through the chemical treatment. And next, the VSM analysis. The same image showed the rod-like shape and smooth surface of cellulose nanofiber, which indicate a non-cellulosic content removal after the chemical treatment, and the decreasing gap of ultrafine grinding for the fibrillation resulting the smaller size of cellulose fiber into cellulose nanofiber, which happened due to high shear force that generated during ultrafine grinding process, which breaks cellulose fiber bundles into smaller fibrils. So the decreasing gap in ultrafine grinding resulting a smaller size of cellulose nanofiber, and the smallest diameter of cellulose nanofiber that we obtained in this study are 22.4 nanometer, which achieved through a gap of minus 110 micron with 30 passes using ultrafine grinding method. And next, the X-ray analysis that shows the decreasing crystallinity index after the grinding method, but it also increased as the ultrafine grinder gap decreased. So the decreasing gap in ultrafine grinder could increase the crystallinity of sorghum cellulose nanofiber. So the conclusion of this study are the isolation and characterization of cellulose nanofiber from sweet sorghum bagasse have been successfully done. The sorghum bagasse used in this study contains 35.06% of cellulose, 20.07% of hemicellulose, and 11.25% of lignin. The gap variation that used in this study are ranged from 0, minus 10, minus 30, minus 50, minus 70, minus 90, and minus 110 micron. And cellulose nanofiber with diameter of 22.4 nanometer was produced through a minus 110 micron gap with 30 passes on ultrafine grinder. And next, the crystallinity of CNF produced with a gap size of minus 10 micron are 46.97%, which increased to 57.25% through gap size of minus 110 micron. This result showed that the difference in gaps in the ultrafine grinding could affect the size and crystallinity of sorghum cellulose nanofiber.
Warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. My name is Putri Amanda from Research Center for Biomass and Bioproduct, National Research and Innovation Agency, or BRIN. Today, I would like to present our research. The title is Characteristic of Pickering Emulsion Stabilized by Cellulose Nanofibrils in Different Oil Phase Polarity. This research was investigated by me, Putri Amanda, Setiani Budiari, and Anita Amelia. I think we are all familiar with the miscibility of oil and water, yet within our home are numerous examples that oil and water do mix, like mayonnaise, butter, shampoo, day cream, cleansing oil, or even a supplement. This example represents a specific category as a mixture known as an emulsion. And what is an emulsion? Emulsion is a thermodynamically unstable system containing mixture of two or more immiscible liquid which is stabilized by adding emulsifying agent, or we often say as a surfactant. However, solid particle can also be used as an emulsifying agent, and for this emulsion system, it's known as Pickering emulsion. For more detail about this, we can see at the picture. As I mentioned before, in Pickering emulsion, solid particle is used as stabilizer, or we can say we didn't need a surfactant. And because of this emulsion didn't need a surfactant as stabilizer, Pickering emulsion, also known as a near surfactant emulsion. Various particles can be used as stabilizer like inorganic or organic particles or even nanoparticles. Nanocellulose like CNF or CNC is one of the best solid particles can be used as stabilizer because they have many advantages such as high aspect ratio, availability properties, and of course nanocellulose is environmentally friendly materials. In the emulsion system, the interaction of the oil phase and the particle used to prepare the emulsion are essential factors that affect the stability and sometimes also affect the emulsion time. For many emulsion products that I mentioned before, we can see that the emulsion can have various structure like liquid form or more thick emulsion such as a gel or a cream. Moreover, we know that in our daily life we often find emulsion products that break down during the storage. It's interesting. Why did this happen? why emulsion can have various structure, or why emulsion can make or break? The answer is because the interaction of stabilizer with the oil phase and the emulsion system. This means if we want to learn what is the best oil phase that can be matched with a solid particles or vice versa, we can vary the oil phase polarity. So the objective of this research is to know what is the most suitable oil phase for CNF as stabilizer to make a stable Pickering emulsion. We investigated the characteristic of Pickering emulsion in different oil phase polarity. To know about that, we investigated the characteristic of Pickering emulsion stabilized with CNF using two parameters. First, effect CNF concentration on emulsification process, and second, effect oil phase polarity and stability of Pickering emulsion, justified by viscosity, droplet size, and creaming index after emulsion storage. For experiment, we use CNF with solid content 1.5% with various concentration and emulsion system from 0.5 to 2% weight per volume. We use 3 model oil with different polarity, ethyl acetate, toluene, and hexane. We use ultra-turab for emulsification process and microscope and Brookfield viscometer for further characterization. First one, effect of CNF concentration on emulsification process. As I mentioned before, we use 3 solvent oil with different polarity as a model oil. Figure 1 shows that the visual observation of the emulsion after preparation with various CNF concentration. We can see that one of the key reasons to successfully stabilize of the Pickering emulsion is the concentration of the CNF. The emulsification process hexane emulsion is the lowest and the lower concentration of the CNF, unlike ethyl acetate and toluene emulsion. There is no emulsion formed in 0.5% of CNF. This is because a fewer particles are sufficient to stabilize a less polar of oil phase droplet and make the interior structure collapse owing to its own gravity. Physical characteristics of the resulting emulsion were used to characterize the effect of oil phase polarity on the Pickering emulsion stabilized by CNF. They are viscosity, droplet size, and creaming index. The first characteristic is viscosity. Most emulsifiers operate with both polar and non-polar oil, although each has unique preferences. This means that some emulsions perform better with more polar oil than the others, or vice versa. So, the polarity of the oil employed in an emulsion can significantly impact its viscosity and the stability. Figure 2a shows the viscosity of the emulsion in various polarities 1 hour after preparation. The results show that the emulsion viscosity increased as the polarity of the oil phase decreased, or emulsion from ethyl acetate oil phase less viscous than hexane emulsion oil phase. Furthermore, to investigate the stability of emulsion, the change in viscosity of the emulsion was observed during 30 days of storage. We can see at the figure 2b, the viscosity of all emulsion decreased during the storage, with the most significant decrease occurring in the emulsion with oil phase was ethyl acetate. Or we can say the most stable emulsion is hexane and water emulsion. According to finding of the study, lower polarity solvents undergo less viscosity loss during storage than higher polarity solvents. Lower polarity solvents are more stable for droplet development than higher polarity solvent because the interfacial tension of oil and water is high, allowing particles to adsorb strongly to the droplet surface and inhibit droplet coalescence, resulting in a smaller change in viscosity and, of course, more stable emulsion. The stability of emulsion also investigated based on droplet size of emulsion system. A droplet size was measured using imaging from optical micrograph image, and we can see the result on the figure 3. The results show that the emulsion with the higher polarity of the oil phase have higher droplet size than the emulsion with lower polarity. The droplet size decreases if decreasing oil phase polarity. Or we can conclude that CNF or nanocellulose is more successful in stabilizing the interface in non-polar oil phase than the polar oil phase. Then we also investigated the differentiate of droplet size during the storage, and the results show in figure 4. We can see that the emulsion with less polar solvent experienced the lowest droplet size change during storage, and it is in line with the previously reported change in viscosity. Its midlife extent in water emulsion stabilized with CNF more stable than other oil phase polarity emulsion. And for the last, we also investigated the creaming index of emulsion in 1 month storage. We did this in order to gain a better understanding of the stability of the emulsion system. The data are presented in figure 5, and the data show that emulsion with higher polarity of oil phase have higher creaming index, indicating lower emulsion stability. And this is conclusion for our research. From this research, we know that we can easily change the Pickering emulsion viscosity and stability depending on the product concept and requirement by looking at how the particle stabilizer interact with the polarity of the oil phase. For Pickering emulsion stabilized with CNF, the Pickering emulsion stability to emulsify depended on the CNF concentration in all type of oil phase polarity. The Pickering emulsion viscosity and droplet size change with polarity, and the stability of the heavily depends on the polarity and the oil phase. Hexane in water emulsion has less change in viscosity, droplet size, and creaming index after storage than the others, indicating better stability than the others if stabilized with CNF.
Ladies and gentlemen, in this beautiful day, please allow me to present you our research with the title of the research is Preparation and Characterization of Cross-linked Biohydrogel from Oil Palm Empty Fruit Punch. The background of this research is because the enormous of the oil palm empty fruit punch as a waste in Indonesia. According to BPS data in 2021, the plantation of oil palm more or less than 14.6 million hectares, and it caused the oil palm empty fruit punch or OPEFP in average per year almost 6 million tons per of waste. The oil palm empty fruit punch were known still have a high content of lignocellulose. Those lignocellulose can be separated using delignification method to separate the lignin and the pulp or cellulose. The cellulose that were isolated can be utilized to make a form of a biohydrogel. And our research, we utilize those waste into a biohydrogel form that can be used and developed in daily use. The utilization of a hydrogel we can use as a dye absorption, artificial snow, biomedical thing, or bioremediation. In this research, we had 3 main stages of method. First, we pre-treatment the OPEFP that we use are physical chemical treatment to delignificate lignocellulose and isolate the alpha cellulose using microwave and autoclave instrument by 2 types of solvent that we use is acid and alkaline. The second stage were synthesis to make a biohydrogel using the alpha cellulose that were isolated. We dissolve into a combination of solvent that has natrium hydroxide and urea at the temperature minus 13 degrees Celsius, and we add the natrium carboxymethyl cellulose with various of concentration, and we add the epichlorohydrin as a cross-linker agent, and we stir until homogeneous, and we keep at the temperature of 4 degrees Celsius for 24 hours. The last stage is the neutralize step. So we neutralize the biohydrogel using an aqueous until it's neutral. The result of this research indicates that the addition of sodium carboxymethyl cellulose can cause the formation of a matrix in biohydrogel. The surface of color from biohydrogel before and after neutralized is because of the base group in the biohydrogel before it's neutralized need to release with the aqueous. The control sample that without the addition of sodium carboxymethyl cellulose with 5% of epichlorohydrin shows unsuccessful biohydrogel form. The tissue in the biohydrogel, after we analyze the swelling capacity, will swell after being immersed in water for some times. In this research, we took 3 days of immerse time. And as the swells continue, there is a dissociation of ionic group in this biohydrogel. The sodium ionic group from sodium carboxymethyl cellulose during the cross-linking process can increase the swelling capacity. The optimum sample of this research shows in the sample A that with a variation of epichlorohydrin and sodium carboxymethyl cellulose is 5% and 1.75%. It shows at the 630% of gram per gram from swelling degree, while the others could only takes until 300% of gram per gram. The determination of cross-link percent degree from biohydrogel shows a great ability of cross-link. Most of the sample shows cross-linking percent in 90%. This shows that for every gram of biohydrogel form, the binding ability of the cross-linking is in the range of 90%, which is successfully cross-linked to the formula. With the modification of the extension polymer chains, then chloroform as an extracting agent for polymeric materials does not able to extract hydrogel or biohydrogel materials with good cross-linking ability. Chloroform ability in extracting the remaining materials of the biohydrogel formulation, resulting in the biohydrogel form after being extracted with chloroform, did not decrease its shape and weight after being extracted to the initial weight or weight rate. As you can see here, we had the lowest determination cross-link is sample D and sample I. The pattern of spectra infrared have proven that isolated cellulose from OPEFP and adding natrium carboxymethyl cellulose were successfully cross-linked with epichlorohydrin and made a biohydrogel. It shows at the peaks on the wave number 13 and 28 belong to the new form group after becoming a biohydrogel. The morphology of biohydrogel were shown by scanning electron microscopy, and it shows the hydrogel D still had a lot of cellulose that unreacted, while the 3 of hydrogel that representative shows the homogeneous surface area. In conclusion, based on the research conducted, it can be concluded that the biohydrogel cellulose-based cross-linked epichlorohydrin was made by addition of natrium carboxymethyl cellulose as a matrix, with the optimum formulation were shown on sample A that have 1.75% of natrium carboxymethyl cellulose and 5% of epichlorohydrin as a cross-linking agent. And it showed that the swelling capacity of the sample A is 630% of gram per gram. Thank you so much for your attention.
Okay, that's all of 5 video presentation this session. So now is Q&A session. If you have any question, you can deliver directly to the presenter. Already here, all of the presenter, right? Because if not, the committee will drop the paper, yeah.
Yes, of course. We must stay here to represent the Q&A short session.
Any question from the participant?
Actually, I have a question, but if there is any question from the participant, it will be firstly to deliver to participant.
To whom?
Okay. Firstly,
You have question?
okay. I have my sound is clear.
Yeah, it's clear.
Okay, thank you very much. I have a question for maybe for early presenter. My question to Mr. Adi. Teak is an expensive species. There must be a very reasonable reason why teak was chosen. Is there anything special about teak in your study? Why you don't use west teak maybe, or the other one kind of wood with not too economically wood? And then the second one, my question to Miss Aisha, for what kind of application will cellulose acetate with characteristics like in your research be used? Maybe you can directly explain what kind of the application of your cellulose acetate. And to Miss Don Pedro, about crystallinity index, is there a minimum and maximum limit so that it can be used as reinforcement to composite? And then the last one to Ms. Putri, I want to relate with hydrophobicity. When we are going to develop a coating material based from cellulose, what kind of solvent that you use from your research? I think for question maybe like this. Thank you.
Okay, thank you, Mas Adik, for your question. Okay, we can start with answer saja. We start with Pak Adi, please.
Okay. Thank you for your question, Mr. Adik Bahanawan. And I agree with you that the tick species is expensive and it has multiple benefit, right? But beside the contribution to circular economy, in the silviculture system, there is a thinning process. It's mean that a little plantation it cut off, and then to give more opportunity to other plantation to develop their yield. So in that case, so in my recent study, we use the residue of thinning process. So I think it's very beneficial to the environment. So it will decrease the residue in thick plantation area. Thank you for your question.
Thank you, very clearly.
Thank you, Pak Adi. One more question from me, please. Does it wood in this current study you use wood, right?
I beg your pardon?
Yeah, in this current study, your current study, you use thick wood, yeah? Is it right?
Yes.
I mean,
yes.
Does each wood species have different carbon absorption properties compared with other species?
Oh, no, Dr. Jamal, I only use one species in the current study, so I have no comparison with the other species of thick.
Oh, okay. And the last one, sorry. Yeah. I want to talk about original biocharcoal made from thick wood. Is it made? Does it meet the CORC standard? CORC standard?
No.
Heard about that? CORC.
I can hear your voice clearly here. Sorry.
CORC standard. CORC standard. CORC standard. Does your biochar meet the standard? CORC standard.
Yeah. It's meet the CORC standard, right?
Oh, okay. So I have challenge. I mean, we have challenge from some people. So I will ask you. I will invite you to discuss more on Monday, right? Next Monday. Okay.
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 Thank you.
Thank you.
Dr. Jamal. Thank you.
Okay. Next, Miss Aisyah, you can answer Mas Adi's question, please.
Yes, thank you for the question, Mr. Adik. In this research, cellulose acetate can be used in the various industry, and then in this research is used to be bioplastic. Thank you, Mr. Adik.
For me,
Thank you, very clear.
And
Miss
thank
Aisyah,
you, Mr.
yeah.
Jamaluddin Wahid.
There are lots of research work on the topic very similar with you.
Bioplastic.
Yeah.
Yeah.
I read this morning at least 6 journal very similar with this. My question is, what is your differences with others, and what is your novelty? Hello?
Yeah, yes, Mr. Jamaluddin. The novelty from my research are in the step hydrolysis from cellulose to cellulose acetate. There are the various ratio from water ratio to cellulose, and then the time and the temperature process.
Okay. Okay, thank you, Miss Asia. The next question. Yeah. Don Pedro.
Okay. Thank you for Mr. Adik for the question about the crystallinity index of cellulose fiber. So from the several literature that I have read about the cellulose nanofiber, it's mentioned that the cellulose nanofiber have a crystallinity index range from 50 to 65%. And in our paper, we have reached highest crystallinity index that is 57.25%. I think. Yes.
So that it can be used for reinforcement to
Yes, for the application in the reinforcement agent, I think it's high enough for applied.
Yeah. Okay. Thank you very. Thank you, Mr. Jamaluddin.
Thank you, Mr.
Yeah, no worries. Thank you, Don. But I have one chat also for you. Sweet sugar, sweet sorghum content very high sugar, right? Yeah. So why are you more interested in isolating the CNF than sugar production?
Okay. Maybe for the raw material that I use in this study is the sweet sorghum bages, that the sorghum juice have been extracted and remain its bages, and I more interested in isolate the cellulose fiber because I think to produce sugar from the cellulose that is carbohydrate complex is maybe need a further treatment than producing cellulose, and its application maybe it's more various if I isolate the cellulose nanofiber.
Okay, so did you isolate the cellulose and nanofiber after extracting the sugar content, or directly from fresh cane?
I extracted from the bagasse, not the
from
from.
Okay.
Yes. Yes. Okay.
So the next question to Putri, yeah. So Putri, your time to answer.
Okay, thank you very much for Mas Adik for the question. The question is about hydrophobicitas. what material can we use for a solvent if we use a cellulose for a material, right? For a coating material. Maybe in my research and pickering emulsion is most usually as cosmetical and pharmaceutical fields. It's not to coating material. So I think I need time to literature review to know what the best solvent that we can use for coating material for hydrophobicity coating material. Okay.
Okay. I think it's very quite different enough because in cosmetic we need to more hydrophilic. Yeah.
Yes.
Okay. Thank you very much.
Okay. Thank you.
Okay, but my question, Putri, what is the advantage of using CNF for stabilizing PA compared to other stabilizer?
Okay, thank you, Pak Jamaludin. Okay. The best thing about pickering emulsion is we didn't need a surfactant or emulsifier to use to make an emulsion system. So we know that like a twin, span, or any other surfactant is they have disadvantage for the product that we want to development. And pickering emulsion, we say it as a near surfactant emulsion. So we didn't need a surfactant, and solid particle like CNF is more environmental, high aspect ratio, and we just need a little concentration as CNF to make emulsion a stable emulsion.
Okay, but is it easy to get CNF right now?
I think yes. CNF is like before research, we can use mechanical treatment to produce CNF, and maybe CNF is need more energy because we need like ultrafine grinder or but because in pickering emulsion we just need a little concentration to make a stable emulsion. I think it's okay. We use CNF for ultrafine grinder.
Okay, thank you for all of answer. So there's a time about 14 minutes, Pak Adi. Is it true?
Yeah.
So we have 14 minutes for discussion. If you have still a question, please deliver address to presenter.
We have maybe about 10 minutes again.
Yeah.
Mr. Jamaluddin. No, it's maybe similar research about between Miss Aisyah and Miss Nabila. So can I see Miss Nabila? Aska Nabila. There is no?
Yes, I'm here, Mr.
Okay.
Any other question?
Yeah, about biohydrogel, maybe you can. I have a question, maybe about how we can conduct about because my research about transparent wood that mostly I'd like to conduct more about optical characterization of transparent wood. So what maybe there is any opportunity to characterize biohydrogel with optical material, and if there is any opportunity in that field, what kind of application, furthermore application to deliver biohydrogel by approach optical characteristic, optical properties, maybe like this. Mr. Jamaluddin and Ms. Aska, can you hear my voice?
Yes, I can hear your voice, and thank you very much for your question. To reach the optical for the application of biohydrogel to the optical field, I still need to learn more about the optical field. I just only know the characteristic using the optical for the optical research in the refractometers, I guess.
Okay.
For transparent the translucent that from the biohydrogels. So basically, our biohydrogel now on currently research for the what it's called as the concentrate and the bioremediation absorption for the soil. So for the optical field, learn more about that. I'm so sorry because I still need of the optical research and what the characteristics that I can use to applicate the biohydrogel.
Okay. Thank you. Maybe can you mention that there is any opportunities to biohydrogel to become more application in food and beverage? I think like bacterial cellulose that maybe more advanced in food and beverage application. How about biohydrogel?
Biohydrogel that using another of cross-linking agent, it's maybe can be used for the food and beverage. But in our research for the biohydrogel that using epichlorohydrin, need more characterized and more study about epichlorohydrin use that use. But if the biohydrogel that use such as a chitosan or something, it can it can use to food and beverage.
So it can be digested with human body, yeah?
Yes, if using chitosan or something else. But if using epichlorohydrin, maybe it used for the environment only. Due to lack of this organic thing that I have heard about the epichlorohydrin.
Okay, thank you, Mr. Jamaluddin. Thank you.
Okay, no worries. Oh, thank you, Aska. Oh, sorry. Yeah, Aska, yeah.
Yes.
Aska, yeah. Talking about cross-linking, your research show that the cross-linking content, 93, more than 90%, right?
90%. It shows most of our biohydrogel is 90%.
So we can say that your hydrogel is cross-linker, is it?
No, it's already cross-linked. So it means the cross-link that we synthesis using the epichlorohydrin is successful.
Oh, okay. Yeah. Because the cross-linker is one important component for gluing, yeah, for adhesive substance, right?
Yes.
Yeah.
Yeah, we familiar with citric acid, maybe like cross-linker. Okay.
Yeah, still 5 minutes, I think, Pak Adik. Yeah. Is there any question from other participants, please? We can optimally the time.
Participant to participant, please welcome. There is any question?
Yes, really to discuss what we've have in our study.
Maybe there is no question again. We can.
Yes, enough. I think thank you for all participants and the presenter this session. So we can close, I think. And I have decide who is the best presenter, but I will not talk here. I will report to the committee. Okay, thank you for your attention, and we can finish this session with saying Alhamdulillah, Assalamualaikum wabarakatuh. See you. And what time will you start again?
We will bring back 1:30, sir.
1:30.
1:30, sir.
Yeah.
Okay, sir.
We're going back
after Jumat pray.
Yeah. Thank you.
Thank you very much.
Thank you very much, all participants, Dr. Jamaluddin Malik and Mr. Adik Bahraman. We can continue the second session at 1:30.
So we can leave the room, or we just.
I think we still in this room.
Okay. Okay.
Okay. Thank you.
Yeah, we hope all participants stay with this room.
Yes.
Okay.
Yes.
Thank you very much, Mr. Jamaluddin.
Thank you. Thank you, Pak Jamal.
Recording stopped. Recording in
It is
progress.
1:30 already.
Hello, okay, Pak Jamal.
Yeah, so we can start.
Okay, I think we can start.
Yep. Before starting, so like before, we can see the short view of all presenters. Yeah. Okay, ladies and gentlemen, we can start this session. Is it not sound, Pak Nuzul?
I can hear clearly, Pak Jamal.
Oh,
I can hear you. Okay, it's clear. You can see the short bio.
yeah.
Okay, thank you.
Yeah, the first presenter is Bapak Suroto Hadi Saputra. He is a researcher at the Research Center Biomass and Bioproduct. He graduated from Faculty of Forestry Mulawan University, and his current research are mainly about non-timber forest product. Then the next presenter is not moving, Pak. Hey, yes, Professor S. Hermiati. She is researcher at the Center for Biomass and Bioproduct, BRIN. She graduated from IPB University, majoring agricultural technology in 2012. And current research is mainly on the conversion of hemicellulose fraction of the cellulose biomass to fully added products such as cellulose, oligosaccharides, and xylitol. The third presenter is Dr. Yeyen. She is the leader of biopolymer research group at Research Center for Biomass and Bioproduct. Her current research focus on sustainable polymers as an alternative to the non-degradable and fossil-based polymers. Currently, her research group has been collaborated with several companies such as Waste for Change, Everywhere, and PT BRIN. And the next, Benedetta Ayu Widyaningrum. She has come from Research Center from Biomass and Bioproduct BRIN. Ningrum current research are mainly on adsorbent material and sensor. And the last but not least is Rohma Pari. She is graduated from she's student, master student in I know her master student in IPB University. Her current research are mainly on physical and mechanical properties of timber. That's all 5 our presenter for this session. So we can see all of presentation by watching the video. But I think the author or the presenter should be here, all of them, right, Pak Nuzo? Otherwise,
yes,
the committee will
Pak
drop
Jamal.
the paper from continuing publication process.
Yes, because in the Q&A session, the presenter must be here.
Right. Yeah. So please show the video, Pak Nuzo.
Okay, thank you, Pak Jamal.
No voice, no sound, Pak Nusuk.
Ladies and gentlemen, I
Okay.
will present a paper with the title Effect of Conversion Method on Fluorescent Tapping Yield of Dipterocarpus grandiflorus. Suroto Disaputra, Andrian Fernandez, and Rizky Maharani. Outline presentation, introduction, material and methods, result and discuss, conclusion. Introduction, Dipterocarp species dominate lowland tropical rain forest in Kalimantan, Dipterocarpus sp. In Kalimantan, there are 27 species of Dipterocarpus sp. Some of Dipterocarpus produced resin have been grown in East Kalimantan, such as Dipterocarpus gracilis, Dipterocarpus grandiflorus, and Dipterocarpus verrucas. Dipterocarpus spp produce derived products in oil and oleoresin, Dipterocarpus gracilis, Dipterocarpus grandiflorus, and Dipterocarpus verrucas. Tapping Dipterocarpus in Cambodia by burning in tapping holes, and in Thailand without burning in tapping holes to obtain oleoresin. Therefore, it is necessary to determine effect of combustion on the yield of tapping Dipterocarpus grandiflorus, oleoresin, and its physical quality in the parameters of specific density and color properties produced. Material and methods. Materials: 2 pairs of the grandiflorus trees, 1 pair of trees with a diameter of 45 centimeter, and 1 pair a diameter of 50 centimeter, and both. Method 1 until 8 to calculate the overall resin yield, the yield from the 2 tapping on occasion were combined. This study aimed to determine effect of combination method in Dipterocarpus grandiflorus tapping holes of phylum, specific gravity and color change of oleoresin yield. Result and discussion. Effect of tapping hole burning on the phylum of tapping yield. Method, 2 method, not burned and burned. 3 diameter, brand-free height. Phylum, not burned, 161.36 and 1,161.66. Barnet phylum 147.08 and 862.37. Effect of tapping hole combination on the specific gravity of oleoresin. Method, 2 method, not burned and burned. The 3 diameter, 1 height, same. Phylum 0.94, 0.95, and burned 0.96 and 0.97. Effect of tapping hole combination on fluorescent color. Two method, not burn and burn it. 3 diameter and burn free height to same. Lightness 79.0 and 45.0. Redness 4.60 and 5.0. Yellowness 17.0 and 24.50. Barnet same, the 3 diameter and burn free height. Lightness 11.0, redness 3.50 and yellowness 8.50. Light 12.50. Redness 2.50 and yellowness 7.0. Conclusion: the yield of fluorescence from the barnet and not barnet tapping method, the first diameter above 50 centimeter was 862.37 mil and 1,161.66 mil. Diameter of above 40 centimeter was 647.808 mil and 1,061.36 mil. The specific gravity of fluorescence in the barnet and not barnet tapping method of the first diameter above 50 centimeter was 0.97 and 0.95. Diameter over 40 centimeter was 0.96 and 0.64. Color of fluorescent tapping method, barnet and not barnet. The first diameter above 50 centimeter, like 11.6, redness 2.5 and yellowness 7, and like 44, redness 5 and yellowness 24.6. Diameter above 40 centimeter, fluorescent color is like lightness 11, redness 3.5 and B, and yellowness 8.5 and lightness 59, redness 4.6, 4.5 and yellowness 70. Thank you for all.
Good afternoon, all participants of ICONLIG 2022. I would like to present our study entitled Preliminary Study on Hydrolysis of Sugarcane Trash Hemicellulose by Inorganic Salt Catalyst for Cellulose Production. Sugarcane trash is an underutilized biomass which is abundantly available in sugarcane plantations. The utilization of this biomass is still limited, for example, for goat and cattle feed, especially during dry season. Sometimes the biomass is burned in the field, and this creates an environmental problem. Grass contains quite high amount of hemicellulose, so that it could be a potential biomass for producing hemicellulose-based products, especially silane derivatives such as silo-oligosaccharides and xylose. Xylose could be used as low-calorific sweetener, while silo-oligosaccharides could be used as sweetener, prebiotic, antioxidant, etc. These bioproducts are still imported and have high prices. The objective of this study is to get preliminary information about the effects of type and amount of inorganic salt catalysts, heating methods, and hydrolysis media on the solubilization of sugarcane thresh, as well as the production of xylose. The materials and methods in this study. The material sugarcane thresh was obtained from Pabrik Gula Jawali 2, Subang, West Java in July 2019. The biomass was going through size reduction processes such as chopping, grinding, milling, and continued with sieving process to obtain feedstock with particle size of 250 and 420 micrometers. The sugarcane thresh goes through hydrolysis process using water or oxalic acid. The mixing ratio or solid liquid ratio is 1:10. Inorganic salt consists of aluminum sulfate and ferric chloride was added at the 50 and 100 micromole per gram biomass. The heating process is conducted in autoclave and microwave. The autoclave is at 120 degrees C for 30 minutes and in microwave at 180 degrees C for 5 minutes. The products was filtrated to separate the soluble fraction and the solid fractions, and from the filtration we get the hydrolyset. Then the hydrolyset was analyzed for its reducing sugar, xylose, and silo-oligosaccharide concentrations. The solubilization of biomass was also determined. Here we can see the results of a chemical composition analysis of sugarcane thresh. This shows that the sugarcane thresh contains high amount of carbohydrates. Alpha cellulose is about 31.47% and hemicellulose 24.34%. Hydrolysis in an autoclave resulted in lower solubilization of sugarcane thresh than hydrolysis in microwave digester. This is probably due to more soapy conditions during the process of using microwave digester. The solubilization of sugarcane thresh in water medium is lower than using oxalic acid medium. The addition in organic salt catalyst slightly increases the solubilization of sugarcane thresh when the process is performed in water. But when we use acid, the tendency is different. When using aluminum sulfate catalyst, it increases, but when using ferric chloride, it decreases. In microwave digester, the tendency is different. Both catalysts could increase the solubilization of sugarcane trace. The reducing sugars obtained from the hydrolysis in water medium is lower than those using oxalic acid medium. In water, oxalic acid, oxalic acid, oxalic acid, oxalic acid. However, the effect of catalyst on reducing sugar concentration in both heating methods is quite different. Regarding the production of reducing sugars, aluminum sulfate catalyst is more effective for the process in acid medium using an autoclave or in water medium using microwave digester. While perchloride catalyst is more effective for the process in oxalic acid medium, either using autoclave or in microwave digester. Xylose concentration in the hydrolyzed with water medium is lower than those with oxalic acid medium. The effect of catalyst on xylose concentration in both heating methods is also quite different. The effect of catalyst could only be seen clearly when aluminum sulfate is added in microwave process or when perchloride is added also in microwave process with oxalic acid medium. There are still some silooligosaccharides present in the hydrolyzed. This means that the hydrolysis needs more severe conditions to hydrolyze the silooligosaccharides to xylose. In water medium, the higher xylose and silooligosaccharides yields was obtained when 100 micromole of aluminum sulfate was added. In oxalic acid medium, the higher xylose and silooligosaccharides was obtained when no catalyst was added. Further conclusions: inorganic salts such as aluminum sulfate and perchloride can be used as catalysts for the hydrolysis of hemicellulose in lignocellulosic biomass. The catalyst could increase the solubilization of chemical components in sugarcane trace, as well as increase the reducing sugars and xylose concentrations in the hydrolysis. Of the two catalysts used in this study, aluminum sulfate is more potential for the production of xylose or silooligosaccharides, especially if the hydrolysis is in water medium using a microwave digester. The xylose concentration obtained from this process is still lower than that from hydrolysis in an oxalic acid medium. Further study on the use of aluminum sulfate at higher amount and with water medium and microwave heating is needed to increase xylose recovery from the biomass. This study is part of JUSTIP project and LIPI-DIPA project 2021. The authors gratefully the Integrated Laboratory of Bioproducts for its facilities as well as scientific and technical support. Thank you very much for your kind attention.
So hello everyone, today I would like to present one of our research which is about the effect of reducing cyanide level in the bitter cassava or manihot esculentacrans on the starch content. My name is Liliana Hamia and I'm one of the author of this research. So bitter cassava or poisonous cassava is one of cassava varieties that has high content cyanide, which contains similar starch content as the starch edible cassava and corn and lactose. The example of bitter cassava known in Indonesia is rubber cassava or singkong karet, singkong puru, and singkong pucuk biru. Bitter cassava known to has high cyanide level is more than 100 mg per kilogram and starch content more than 90%. Based on Food Agriculture Organization or FAO, the limit consumption of cyanide for human is less than 50 mg per kilogram in raw material. So bitter cassava exceed the safety level of cyanide for human consumption. So the consumption of cyanide will bring a negative impact to health. So that's why various methods have been applied to reduce the cyanide level on cassava, which is submersion in water and heating. This variation of method were applied because cyanide is volatile or soluble, so it can reduce the cyanide level. However, it is important to ensure this method does not damage the starch content. Based on our knowledge, there has been no research on the effect of soaking and heating treatment on starch content and its relationship with cyanide levels in bitter cassava. So we received cassava in the field in Cibinong, and also we bought several bitter cassava in Bandung. And then the cassava tubers were peeled and sliced with a thickness approximately 1 cm and then washed with water and repeated 3 times. The cassava was soaked in reverse osmosis water with duration of 0, 24, 48, and also 72 and 96. After that, the cassava blended, and then the slurry cassava was squeezed using a filter cloth with the dimension of 50 to 50 cm. And the squeezing was repeated up to 3 times until the water solution is clear. The cassava solution was left in huge basin for 24 hours, and the precipitate was filtered and dried using oven for 5 hours at 60 degrees Celsius. Then the starch was weighed and stored in a closed container. And for heat treatment, after the starch preparation, the cassava were heat with various temperature, which is 25, 30, 45, 60, and also 75. And for the characterization, we have 4 different characterization, which is the determination of cyanide using Bradbury method, the determination of starch content using log scale method, determination of amylose and amyloid pectin using IRRI method, and also Fourier transform infrared or FTIR. So for determination of cyanide using Bradbury method, first, we prepare picrite paper with the immersion of filtered paper to picric acid solution. After that, 1 gram of sample was weighed in a test tube or clear glass, and then a picrite paper was hung inside the test and closed tightly at room temperature. After 24 hours, the paper was immersed in distilled water for about 30 minutes. And then the solution absorbance was measured in ultraviolet spectrometer at wavelength 500 and 10 nanometers. And we can see this is the various cyanide content in raw materials. The highest is a pucuk biru cassava, and the lowest is potato, which has less than 1 ppm. For determination of starch content, we use log scale method. First, we prepare the filtrate. 2 grams of sample was weighed and placed in a beaker glass. Then 50 ml of distilled water were added and stirred for 1 hour. The sample solution was filtered using Whatman paper, and distilled water were added to the filter until obtained 200 ml. The participate and filter paper were dried in the oven for 1 hour at a temperature of 60 degrees Celsius. Then the participate dried and charged into a 200 ml aluminium. Then 40 ml of 3% chloric acid were added. The solution were flaxed for 1 hour, and then the suspension was neutralized with 30% of sodium hydroxide. After that, the solution was transferred to a 100 ml measuring flask. Then the still water were added. The solution was then filtered, and the filtrate was used for analysis. After that, 10 ml of filtrate was put into an aluminium. 25 ml of luster solution and 50 ml of distilled water were added, and the mixture were boiled for 10 minutes. Then, after that, the mixture were cooled down immediately with ice cube. 15 ml of 30% potassium iodide and 25 ml of 25% sulfuric acid were added. And then solution was titrated with 0.1 Na2S2O3 until light yellow. 2 ml of 1% starch indicator were added and titrated again with sodium thiosulfate until the color changed into white. And then the starch content for various raw material, we can see the highest starch content was detected in the pucuk biru cassava, and then after that in the commercial cassava, and then potato, bitter cassava in Cibinong, bitter cassava in Bandung, and then corn. For the determination of amylose and amylopectin, we use IRI method. First, 200 mg of sample were added to the sodium hydroxide, 1N, and was heated for 10 minutes. Distilled water were added into 100 ml volumetric flask, and 5 ml of solution was placed and added 2 ml of iodine solution and 1 ml of 0 and acetic acid. And then the solution was shaken until it becomes set for 20 minutes, and then the color was measured, the intensity using spectrometer with a 620 nanometer. Amylose was calculated with standard curve equation, and amylopectin was calculated from the formula 100% minus amylose. After the heating treatment, the cyanide content were varied, while the starch content were reduced slightly. And then after that, with the soaking treatment, the cyanide content were reduced significantly, while the starch content were reduced slightly. And the highest starch content is with the soaking treatment for 24 hours, and the cyanide content is in the 10.62 with the soaking for 96 hours. And from this conclusion, soaking treatment much more effective to reduce cyanide while maintaining the starch content. So the cyanide group were detected around 2077 to 2019. As we can see here, the raw material and also the calcium cyanide. So in the raw material, we can see some little peak around 290. And then after the treatment, this small peak were disappeared, as we can see here in the FDIR peaks. So for the conclusion, the elimination of cyanide content in bitter cassava was prepared through soaking and drying. The results show that soaking treatment is more effective to reduce cyanide while maintaining the starch content. The soaking and drying treatment significantly reduce cyanide levels and starch content, but it doesn't affect amylose and amylopectin levels in the cassava starch. Thank you so much for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you for the time that give it to me. Now I want to present our research with the title Effect of Modified Boiler Ash from Sugarcane Bagasse for Mercury Adsorption, Physical and Chemical Properties. We are from Research Center for Biomass and Bioproductive. Research Center for Limnology BRIN, Research Center for Pharmaceutical Ingredient and Traditional Medicine BRIN. For introduction, we know that mercury is one of the most toxic, volatile, persistent, carcinogenic, and bioaccumulation metal that harmful to the environment and human being. The harmful disease of mercury, such as neurologicity, minamata, physiological problem. So we need to reduce the concentration of mercury in the environment. Several methods such as chemical precipitation, ion exchange, membrane filtration, electrochemical treatment, coagulation or flocculation, absorption have been reported and used. And for this research, we choose absorption because it's simple process, high reliability, cost effectiveness, and efficiency. For absorption, we need the absorbent, and we choose raw boiler S or RBA, and then we continue to modify boiler S. Next, material and method. Here we use raw boiler S, and then we modify into three kind of treatment, such as alkali method or AM with potassium hydroxide ratio 1:5, and then the second is oxidized modified or OM. We adopt from hammer method, and then the modified with magnetite or MM. We using co-precipitation method, and the result of this treatment we characterization using instrument like XRF, FSM, XRD, FTIR, and BET. Next, result and discussion. For morphological and BET analysis, we could see the same image here, the RBA and then the modified boiler S. For RBA, we could see the heterogeneous compact crush shape and size. The average pore size was less than 2 nanometer and micropore. And for AM, porous structure, the average pore size was then less than 2 nanometer or micropore. And then OM is regular clear flakes with fraction layer. The average pore size was less than 2 nanometer or micropore. And then for MM, we could see small spherical particle split inside and outside the layer of flakes. The average pore size was less than 5.8 nanometer or mesopore. For FTIR analysis, we could see from the FTIR spectra. Here, RBA has a similar spectrum with AM. This implies that the alkali treatment does not change the functional group. And for OM, only show the highest peak at 1049 and 800. This indicates that SeO2 was dominant, and this result was fitted with the analysis of chemical composition. And for MM, present a new short peak at 630 along with a soldier at 54, and it's contributing to stretching vibrational mode of FAO, functional group of Fa3O4, that covered the surface of boiler S, and this spectra is also confirmed the same image at the previous report. For chemical composition analysis, we could see from the data here that modified or boiler S affected to the percentage of metal oxide, and the result AM has the similar effect with MM. The percentage of SeO2 was reducing and increasing Al2O3, Fa2O3, and CaO. Reduction of SeO2 may be due to the soluble in alkali solution, whereas in MM, the surface of SeO2 may cover by Fa2O3. And next, the oxidation treatment was the opposite of both two treatments. It can increase SeO2 until 89.6%. Next, for X-ray diffraction or XRD, we could see from the X-ray diffractogram, the RBA consists of quartz as a dominant crystalline, that AM and OM affect the intensity at 21 degree which decrease and at 29 degree increase it. And this pattern confirmed by chemical composition like in table 2. And meanwhile, the XRD diffractogram of MM show diffraction peak that's similar with Fa3O4, which indicated that the magnetite covered the surface of boiler S. Next, for comparison of mercury absorption. The percentage removal of different modified boiler ash has been investigated in the PET system with similar condition like initial concentration of mercury 20 mg per liter pH 6, absorbent dose 2 gram per liter, contact time 45 minutes and at room temperature. And the result of the data show that NM exhibit the highest removal, followed by AM and OM. It's due to the surface and porosity of boiler ash are significant factor for the behavior of boiler ash on mercury absorption, and another contribution factor was the pore volume and size. Mesopore with a larger surface area present a great potential for absorption. And here, the conclusion of our research that the treatment affected to the modified RBA, the chemical composition of raw and modified boiler ash obtain same composition but with different percentage amount. The main structure of RBA and modified boiler ash are silica with quartz as the main crystalline compound, and the highest percentage removal of mercury absorption was AN, with 3.6 times greater than RBA, while the OM and MM were 3.3 and 2.3 times higher than RBA. And the results show that the treated material has more effectiveness and economies as an absorbent for mercury ion from an aqueous solution. Thank you for your attention. See you. Bye.
Good afternoon, everyone. Thank you for the time. We would like to present our study about effect of girdling on characteristic of thick wood. The outline of our presentation are introduction, materials and methods, result and discussion, and the last some conclusion. Introduction. Perhutani, as one of the largest wood producers in the world, delivers certified wood for thick wood and non-thick wood. Thick wood has been widely known to be used as material for furniture and construction, and always been in demand because it is famous as strong and durable timber. The stage of thick forest management in Perhutani are determination of cycle time, which has been defined as 80 years. Second, thinning to avoid excessive branching. Third, girdling before logging. And the last, product marketing. On this occasion, we would like to present our study about analysis of wood characteristics of girdled and ungirdled thick wood. Material and method. The main materials used for this study was 80 years of thick wood were collected from KPH Cepu, Central Java. 3 logs with 40 cm length from both ungirdled and 12 mount girdled were taken from each cutting plot. Measurement of physical and mechanical properties refer to British standard for small clear specimen. The physical properties tested were moisture content, density, and specific gravity. And mechanical properties tested were hardness, compression parallel to grain, and modulus of rupture. Result and discussion. Here is the graph of physical properties average value of girdled and ungirdled thick wood. It can be seen from the graph that the physical properties of air-dried thick wood were not significantly different in terms of density and specific gravity. However, the initial moisture content value was significantly different between treatments, with the girdled treatment show 35% initial moisture content, compared to ungirdled thick wood with 78% initial moisture content. It is a fact to reduce the handling cost due to lighter weight of thick wood, effect to the manufacturing process, and effect to the dimension stability. And here is the graph of mechanical properties average value of girdled and ungirdled thick wood. The graph shows that the mechanical properties of air-dried thick wood were also not significantly different, with slightly increase in terms of compression parallel to grain, hardness, and modulus of rupture. It also can be seen from the graph that the hardness value of wood with girdle treatment was slightly higher by 0.2%, and compression strength value was slightly higher by 2%. Meanwhile, the modulus of rupture was 5% higher compared to ungirdled treatment. Conclusion. Several conclusions from our study. First, 1-year girdle treatment reduced the green moisture content by 55% compared to ungirdled thick wood. Second, physical and mechanical properties on air-dry moisture content in this study are not significantly different between treatments. Third, the girdle process is a silvicultural treatment to reduce the initial moisture content of the wood naturally, then more durable and no defect while manufacturing process in order to obtain high-quality thick wood. Last, the characteristics of thick wood with two different treatments in the study were classified as strength class 2. Acknowledgement. The authors grateful to the Perhutani for financial support and also thank to Ministry of Environment and Forestry for the research facilities. Here the reference of our presentation, and thank you for your kind attention. Terima kasih.
Okay, thank you, all presenters. So we move to Q&A session. If you have any questions, please directly deliver.
There is a question. Mr. Jamaludin from
Yes, please.
Miss Aulia maybe.
Okay, thank you, Mr. Adik. My sound is clear? Okay.
Yeah.
Okay. This question for Mr. Suroto. I have two questions. First question is, why you choose forest area with special purpose at East Kalimantan? And then second question is, do you know that potential in Dipterocarpus graniflorus? Why you choose oleoresin? Maybe is done. Okay, thank you.
Okay, who the next? Okay, yes, please.
Hi.
Please, yeah.
Okay, thank you. My question goes to Mr. Suroto. You compare the not burn and burn wood for producing oleoresin. But in the conclusion, you just compare it, but you didn't tell us which one is better for producing oleoresin, either the not burn or the burn wood. Okay, just make it clear. And the second question goes to Dr. Yeyen. I just wondering, the starch content and the cyanide content that you obtain, if we add it, it exceeds 100%. Just wondering why it comes more than 100%. That's it. Thank you.
Okay, thank you. Please. Any other questions?
Okay. Is it my voice clear?
Yes.
Okay. I have a question, Mr. for Prof. Ais. A very interesting presentation, Prof. When you using a catalyst. My question is, is that you get it back after that reaction, your catalyst, I mean. And I just interest when you have a method using hydrolyzing using media, water, and oxalic acid, isn't it? And then I want you to explain why you choose this media rather than you only use with water only. And then next question to Miss Yeyen. Can you explain it to me why you use that method? Is it the novelty or you have another justification for your novelty? And then for Miss Pari, can you explain it to us? Your method, is it your method can apply to another wood or only it's a specific for the classify wood?
Okay. Before beginning, we have 3%, yeah, and with 4 questions, 2 or 3 for Pak Hadi and 1 2 as well for
Mr. Suroto.
Yeah. Okay, yes, please, your answer.
Okay. Thank you, Mr. Jamaluddin, Mr. Jamal. And a question from Aulia for me. Question 1 first. In special purposes forests, they are social forestry. The resin tapping will be one of non-timber forests produced as additional income for village around the forest. We hope in the future growing can be sustainable and not extinct. And tapping not burned and burned in Indonesia or Kalimantan number 1 atau first. Okay, answer question second is Aulia. There are many reference about a tapping method and resin marketing abroad. For example, in Thailand, Laos, and Iran. They also have household or resin industries, but the 3 species are different from the 3 species that produce resin from Kalimantan. Thus, the resin that is probably not similar in Kalimantan. Resin is used for tooth and wood medicine only. If we apply the tapping method adopted from Thailand and Laos, the pterocarpus or growing tree will be dead. And question Mrs. Uis, I am answer. The this is not born because resin film is hanged the burn tapping made the resin color became darker. Okay.
So the better one is the not burn. The not burn is the better one.
Yes, Prof. I mentioned that
Sorry,
the,
I'm sorry.
Yeah, the better one is now the combustion method, maybe. Yes, clear.
Okay, thank you.
Mr. Suroto. Yeah.
I'm sorry, not here.
Okay, it's okay. Adik has explained it.
Okay. Yes, hello.
Yeah.
Okay.
Got it, Prof. Is clear?
Yeah, okay, thank
Okay.
you.
Good. Any other question?
Oh, I have to ask. I have to answer a question from.
Oh yeah, sorry. Yeah, you have two question.
Yeah.
Yeah.
Data asked me why use water only and acid, if I'm not mistaken. So we would like to compare. Usually we compare just water and acid. Now we would like to use the catalyst. So we use water only, and then water and add it with catalyst, 2 amount of catalyst, and we also use acid only, and the acid with catalyst of 2 amounts. So using these experiments, we can compare whether the catalyst could increase the xylose yield if we use the water medium or if we use the oxalic acid medium. And from our research, it seems that if we use water medium, it is more effective. If we use catalyst, this inorganic catalyst, it's better to use just water medium because it could increase the xylose rate. The xylose rate that we obtain with catalyst is higher than if we use just water. But if we use acid catalyst, oxalic acid, if we use oxalic acid and if we add the catalyst into the oxalic acid mixture and we do the process, then the result is getting lower, the xylose yield. So the catalyst is not effective if we use acid as a medium. That's what we would like to know in the experiment. Is that can answer?
Okay,
or any other question?
Yes. And if you using the catalyst, is it you get it back the catalyst?
Excuse me, I could not hear.
Oh, okay. I will repeat. Okay, Prof. When you using the catalyst, is that you get it back the catalyst after the reaction?
Oh.
Yes, please, Prof.
Muted.
Mute, sorry.
Yeah.
We don't so far we haven't get back the catalyst, so the catalyst is still in there in the mixture, and later because the advantage of using this catalyst is that it can be recovered. So probably in the future experiment we have to get back the catalyst, so it could be recycled to be used it again in the new process. So far, we haven't done the recovery of the catalyst.
Okay, Prof. Yeah, thank you so much.
You're welcome.
There is still any question that not be answered?
Mine.
Yeah, okay, yeah. Please.
Okay, so I would like to answer the first question from Prof. Ais. Actually, Prof. Ais, I could not hear you very clearly on the question. Can you repeat it?
Oh, I saw in your table, you saw us the starch content and the cyanide content. And if we add the cyanide content with starch content, it's over 100%. That's
yeah.
I'm just wondering why it could get more than 100%.
Okay. So actually it's not, so the starch content means it's not related to cyanide content. So the starch content is from the, I think it's from the, what's it, sugar? Yeah. Yeah, this was for process. So it's not adding each other. So yeah, it's actually should be not percent. I think it should be ppm. I'm sorry.
Okay.
Yeah. Percent. It should be my mistake.
Yeah. Okay, I think the cyanide content is in ppm.
Yeah, it's ppm. Thank you.
Thank you.
So, and also Mbak Ayu, I would like to answer Mbak Ayu's question about the justification of our research. So actually, I would like to use bitter cassava in a bioplastic because I know bitter cassava is not consumable because it has high cyanide content, and then I have an idea whether there is a correlation between removing cyanide content and also starch in bitter cassava, whether it will be affected, whether the elimination of cyanide content in bitter cassava will actually affect the starch content. And then after some experiment, I got the result that it is affected the starch content, but not significantly. Does it answering your question, Ms. Ayu?
Okay, thank you.
Thank you. Yeah.
Question from Ms. Bernadetta about novelty, about maybe about your methods. Ms. Yayan?
Yes.
Question from Ms. Bernadetta, talk about method in your research about the novelty, maybe about the novelty. Is the
in the methodology for elimination of cyanide content is not new. There's a lot of research regarding elimination of cyanide content using the soaking the tubers or drying starch. However, as far as I know, there's no research correlated between elimination of starch content and elimination of cyanide and the starch content. So that is I think the novelty is on the evaluation or investigation, but the method is similar to others. Yeah.
Okay, Miss, I get it.
Yeah, thank you.
You,
one question to Mr. Ramapari, maybe from Ms. Bernadetta, yeah.
Okay, thank you for the question. Is it clear?
Yes.
The question is the method can apply to another wood? Yeah, the answer is the treatment method can apply to another wood. For example, from previous research, there's research about girdling treatment on acacia mangium, and the result is similar with our result, which the moisture content decreased by 50.8%. And in our research, the moisture content decreased by 55%. Is it clear for the answer?
Okay, Miss, thank you.
Yeah, you're welcome.
So the method will apply for all or other species.
Yeah.
Yeah. Okay. Pak Adik, is this enough for decision because
yes.
14.
Very on time, yes.
Yeah, exactly. Time.
Yes, very on time.
Okay. Thank you all presenter for decision and the question for contribution. So we can move to the next or the last session. It also contain 5 presenters by Samsidar, Jahiding, Desi, Aulia, Khonsa, and Khosa. You can see the short bio. Samsidar is student in Department of Chemistry, Science Faculty Asudini Unhas, Makassar, and current research effect of rice husk cellulose extraction method with addition of prioritization on the physical chemical properties of bioplastic. And then about Pak Jahiding has been a lecturer in the physics study program, Faculty of Mathematics and Natural Science, Halu Elo University, Kendari, since 1994. His research is about material and energy. And then next, Desi is my member in research group. Desi is research of biomass and bioproduct. Then in she was graduate from NU. Her current research are mainly on functional material derived from lignocellulosic material. Next presenter, Aulia. She is researcher at Biomass and Bioproduct Research Center. She is graduated from Jamban University. Aulia's current research are mainly on wood science and forest product technology. And Budi Saksono is PhD from Japan, Kagoshima University. His research about mainly about enzyme engineering. Wow. Yeah, that's all of our presentation. So we can start from the first presenter, please.
Thank you for Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good day, everyone. We are very related at this very important event, the second International Conference of Lignin Cellulose. Let me share the screen. Now, I would like to present my result about effect of rice husk cellulose extraction method with the addition of plasticizer on the physical chemical properties of bioplastic. We are from the Pasadena University. Result background. The problem now isn't only in Indonesia, but it is a world problem. It is the plastic waste handling. It's still a problem because placing plastic in the sea, river, sewer, and housing. Difficult to degrade in soil, contain residual chemical, block in sediment and river water flow, reduce clean water and source of disease. So we need product from natural ingredients like this, raw material, easy to degrade, environmental friendly, abundant raw material. Introduction. As we know that bioplastic have been developed since 2004 in Indonesia, but they differ from the research are new material source and manufacture method. One of abundant raw material is rice husk. Agency for Agriculture Research and Development 2022 rice husk produced 15 million tons every year, or as much as 10 to 20 tons every day. So we can produce this into planting media, biomass, silica gel, charcoal, briquette, organic fertilizer, and raw material for making bioplastic. As we know that rice has chemical content consists of 50% cellulose, 25 to 30% lignin, and then 15 to 20%. And we take the cellulose, so we can make the raw material for bioplastic. Reserve place. The research was conducted at the Biomaterial, Biomass, and Bioproduct Research Center, Biochemistry and Analytical Laboratory, and the Science and Technology Faculty in Alauddin, Makassar. Reserve flow, rice hard, rice husk, clean it and dry. After that, we clean it and dry in the sun, and then crush it and sieve a size 80 mass to equalize the sample size. And then pre-treatment is hard. We use the 3 different methods, and the lignification to remove lignin to rice husk, then obtaining cellulose, and then bleaching. Bleaching cellulose, which is water to make bioplastic. Reserve flow, the rice husk pre-treatment, the different method pre-treatment, rice husk using microwave, and the second autoclave, and the third we maceration. Extraction of cellulose of rice husk by microwave. The same method, rice husk, crush it and sieve. The rice husk 80 mass, and then we took 10 gram rice husk and added the natrium hydroxide 5%, and we put in the microwave bottle, so we into the microwave. Extraction of cellulose from rice husk by autoclave. Rice husk added 5% natrium hydroxide, and then took in the autoclave. So we filter it in refined, was mixed with exposure 30 minutes. We check the temperature in the 180 Celsius degrees. After that, we bleach, and then rice has added 5% natrium hydroxide with ratio 6:1 and put in autoclave. The temperature 121 degrees Celsius for 2 hours. And this cool the room temperature after that separated prepared and residue, and dry 105 Celsius degrees. So the cellulose bleaching to find the weathers. Extraction of cellulose from rice husk by maceration. The sample added methanol for it is the same for the autoclave and the microwave. Rice husk, crush it and sieve, and rice husk 80 mass. We added the methanol. The sample added methanol for 7 days, and the solvent changed every 2 days. The precipitate was washed until methanol free and dry at the 55 Celsius degrees. So 10 gram rice husk sample added the 300 milliliter of natrium hydroxide and natrium carbonate 5% for the liquefaction, and then we separated using heated and filtered and dry 50 Celsius degree. Result and discussion. Bleaching process, we use natrium hypochlorite and the optimal 2% of natrium hypochlorite, and the cellulose we find the 56%. Result and discussion. The second table, average content of rice husk. We see the composition, the lignin 19.12%, and the cellulose 55.68%, and the hemicellulose 80.30%. This is the figure, average content of rice husk. And the third table, average content rice husk pre-treatment variation. The third table, the highest lignin in the microwave. We find the microwave and the cellulose using maceration, 55.68%. And the bleaching process, we see the second figure different in the color of cellulose powder. The A is before bleaching and B is after bleaching. By using microwave is the whiters, then autoclave and maceration. This is the figure. This very right. The mechanical properties analysis. The mechanical property of rice has bioplastic and pretreatment variation. The highest tensile strength is using microwave, 3.96 megapascal, and the lower of elongation, 2 in the microwave. You see 0.554%. Rice has cellulose function group using FTER. FTER spectrum of rice cellulose. This is the rice has cellulose and the red is standard cellulose. We see no difference of FTER spectrum, standard and rice has cellulose. The four figure like that. No differ between the microwave, using microwave, autoclave, and maceration method. And this is the standard cellulose. The third figure, observation of rice has bioplastic morphology at week A, B, C, D, and the bioplastic deterioration up to 3 weeks surface covered fungus, and also getting darkness. Conclusion, sample from rice husk into process of extracting loss were obtained using microwave, autoclave, maceration, pretreatment. Cellulose from rice husk extracted were 55.68%, 50.77%, and then 50.40%. This is maceration, autoclave, and microwave pretreatment. Pretreatment have effect to decrease in lignin content and hemicellulose, as well as an increase in cellulose content in pulp materials, sugarcane. The best treatment in the biggest pretreatment process with 5% natrium hydroxide and 10 microwave exposure, 30 minutes to product whiter cellulose after bleaching. And the later cellulose is maceration pretreatment method, so that the extraction method very influent to physically and chemically of bioplastic. Thank you for attention.
Ladies and gentlemen, thank you for the time and opportunity. Allow me to present my paper entitled The Pyrolysis Temperature Effect on the Composition Process of Bio-oil and Biochar from Coconut Cell for Biocoke Hybrid Application as an Alternative Energy Research. We have 5 members, namely M. Jahidin Masumi, Ersan S. Hasan, F.S. Purnamasari, and myself, Yuku Milian, from Department Physics and Chemistry Faculty of Mathematics and Natural Science, Halu Oleh University, Kendari, Indonesia. Biomass is one of the new and renewable energy source with the potential as a significant energy source in the future. Currently, biomass accounts for around 12% of the world primary energy, while in developing countries, its contribution reaches 40 to 50%. The modernization of bioenergy system plays an essential contributor to sustainable energy development, especially for development in industrialized and developing countries. In Indonesia, biomass is a very abundant natural resource and has the potential to reach 146.7 million tons per year. One of the potential sources of biomass energy in Indonesia is agricultural waste such as KS or coconut shell. The GS is a material that can produce a calorific value of around 6,500 to 7,600 kilocalorie per kilogram, has continued components such as lignin 29.40%, cellulose 26.60%, and hemicellulose 27.70%, containing C, O, H, and atoms. This component indicates that the coconut shell contains a lot of carbon, which has the potential to be used as biocoke. Biocoke is a solid biomass fuel with a high density and strength compared to conventional solid biomass fuel, which can be used as a potential alternative to coking coal. So far, the use of coconut shell has only been limited to charcoal and briquette. In contrast, pyrolysis can produce bio-oil and biochar in one method. Pyrolysis is the thermal decomposition of an organic material, biomass, at high temperature in the absence of oxygen, with products such as charcoal or biochar, bio-oil, and gas. Experimental section. The raw material used in this research is GS from coconut plantation waste in South Konawe Regency, Sute, Sulawesi Province. The GS obtained was first to remove the remaining dirt, then dry in the sun to remove moisture and cut into pieces measuring 5 to 10 centimeters. 500 grams of GS were put into the pyrolysis reactor and then heat at a temperature of 500 to 700 degrees Celsius. The pyrolysis temperature was set using an initial temperature of 120 degrees Celsius for 180 minutes to evaporate the water in the material. Then the temperature was increased to 500 degrees Celsius and maintained after 180 minutes. After that, the pyrolysis temperature was lowered back to room temperature, and the charcoal was removed from the pyrolysis reactor. The procedure was applied to other samples with pyrolysis temperature of 600 degrees Celsius and 700 degrees Celsius. After that, the sample is characterized. Result and discussion. The physical characteristic pH, density, viscosity, and calorific value. Temperature variation significantly affect the formation of the pyrolysis liquid. The higher temperature used, the greater the figure of pyrolysis result. This happens because the cracking of biomass required heat and high-quality fluid product from a fast heating rate of about 500 degrees Celsius. Based on the research, it is known that the effect of temperature on the physical characteristic of GS bio-oil is shown in the following table. Table 1 shows that GS bio-oil has a pH between 2.49 to 3.40. The results show that the quality of bio-oil obtained has high quality. This is caused by several factors, including the increase in temperature in the pyrolysis process. Increasing the pyrolysis temperature tends to increase the bio-oil pH. The high acidity is caused by the pyrolysis process, which breaks down cellulose, lignin, and extractive substance, so the pH of bio-oil obtained is generally relatively high. The obtained bio-oil density value at 500 degrees Celsius are higher than those at 600 degrees Celsius and 700 degrees Celsius. The value of density of bio-oil obtained follow the quality standard of the density of bio-oil for fuel because it the ranks of 0.94 to 1.22 gram per milli. The smaller the density of bio-oil, the better it will be used as fuel because it's lighter. High density can cause incomplete combustion reaction. The result of the viscosity analysis, the higher bio-oil viscosity is at a temperature of 700 degrees Celsius. Viscosity describes the internal resistance of a fluid to flow. This is because the higher the combustion temperature, the viscosity of the bio-oil also increases. So, the lower the viscosity of fluid, the greater the movement of the fluid. The analysis result show the calorific value is almost close to the calorific value of premium gasoline, which is 509 kilocalorie kilogram. This indicates that the increase in temperature has a significant effect on the calorific value. This is figure show the GCMS analysis of bio-oil CS pyrolysis result at temperature A 500 degrees Celsius, B 600 degrees Celsius, and C 700 degrees Celsius. And then Table 2 and Table 3 show that the component of GS bio-oil compound as a result of pyrolysis and that the pyrolysis GS bio-oil product compound phenol, 2-dimethyl phenol, and 1,6-3 propan. Distillate bio-oil contain compound phenol, furfural, 4-hydroxyphenyl phosphonic acid, 2-methoxyphenol, 3-methylphenol, and creosol. In both processes, phenolic compounds are still dominant. Phenol is an aromatic compound with an OH chain and one or more hydroxyl groups. Based on the identification of bio-oil compound, there was a decrease in the H group and increase in the phenol group with increasing temperature. The reduction in the acid group is even lost because of the decarbonylation reaction that breaks the oxygen bonds in the acid group to become an alkane chain. Carboxylic compounds are the most abundant compound in bio-oil because of the large amount of cellulose and hemicellulose in CS. Figure 3 shows the result element analysis of the ADX spectrum of GS charcoal with quantitative ZAP method. Standard at a temperature A 500 degrees Celsius, B 600 degrees Celsius, and C 700 degrees Celsius. Figure 4 and 5 show same image of the GS biochar obtained at a pyrolysis temperature of 500 degrees Celsius, 600 degrees Celsius, and 700 degrees Celsius. However, the biochar show large and clean pores from impurities in figure 4C and 5B, caused by heat energy or the high temperature used during the pyrolysis process, which is 700 degrees Celsius. This shows that the carbonation process occurs when the carbon chain is broken. The clean it is from impurities, the more organic bonds are released. If the biochar is clean of contaminants, the pores will be more numerous and the surface area will be more significant. Therefore, important parameters such as temperature significantly affect the characteristic of biochar and bio-oil. The large pore size of the GS biochar causes the absorption capacity to increase, so that if bio-oil is injected into biochar using the method diffusion or blending, it will be absorbed optimally. This can lead to an increase in the calorific value of biocoke. Conclusion: the effect of temperature on the pyrolysis process is the main parameter, and the temperature of 700 degrees Celsius is the best parameter. The result of this study indicate that the calorific value of GS bio-oil obtained at a temperature of 700 degrees Celsius is close to that of premium gasoline. Biocoke hybrid is formed from biochar GS, which is injected with bio-oil GS so that it will increase its calorific value. This is due to bio-oil's compound content, which is dominated by phenolic compound. Besides that, the bio-oil has the same characteristic as other fuel. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, today, on behalf of the team, please let me, Desi Ramitri Satya from the Research Center for Biomass and Bioproducts of the National Research and Innovation Agency, share with you our interesting findings on the effect of strain dimension and specific pressure on the performance of strain board made from tally bamboo or Gigantocla apus. Did you know that in the last few decades, the utilization of synthetic-based materials caused a range of emerging issues that are shortage of non-renewable raw materials, the environmental problem and health issues, and the uneconomical production cost. Therefore, bio-based materials grow rapidly. Various types of bio-based materials has different characteristics which suit different application purposes. One of the prospective composite panels to be developed is strand board. Strand board is a composite panel made from long and thin strand which bonded using glue through hot pressing. It is commonly used as structural panels for floors, walls, and ceilings, packaging, furniture, and eye-joints. The high interest in using strand board is due to its several advantages, such as cheap, high strength, appropriate dimensional stability, and resistance to surface bulging. Lately, the development of composite panel, including strand board, from non-wood materials such as bamboo becomes a new trend due to the shortage of wood and the massive campaign in reducing deforestation as an effort in decreasing greenhouse gas emissions. Tally bamboo, or Gigantocla apus, is especially interesting to be developed as raw material for strand board. It is because its small rod size, high strength, and its abundant availability. This study will investigate the effect of variation in strand dimension and specific pressure on the physical and mechanical properties of tally bamboo strand board. Tally bamboo was obtained from Bogor, West Java, Indonesia. The combs were cross-cut into 30 to 40 cm long segments without knot, and was split into 2.5 cm wide bamboo strips. The strips were manually sliced with 0.5 to 0.8 mm in thickness, and then cut to 75, 100, and 150 mm long. Strands were then air-dried for 2 weeks, and then oven-dried at 80 degrees Celsius to a moisture content of 4%. The adhesive used was phenyl formaldehyde, wax emulsion, and paraformaldehyde as hardener. A specified quantity of bamboo strands were then mixed with certain amount of phenyl formaldehyde, paraformaldehyde, and wax emulsion in a rotating drum blender. After blending, the resinated bamboo strands were unidirectionally hand-formed into loose mat in a 30 cm by 30 cm wooden decal box. The form mat was then loaded in a hot press set at temperature of 150 degrees Celsius and pressed for 6 minutes at specific pressure of 25 kg per square centimeter or 30 kg per square centimeters. The BSB produced were conditioned for 14 days at room temperature prior to testing. The tests involved in the study including for physical and mechanical properties following Japanese industrial standard GIS A5908-2015. To analyze the result, a completely randomized design with 2 factorial experiment was performed. Here is the result. It can be seen from the graph that all of the moisture content value of BSB satisfied the Japanese standard. The analysis of variance revealed that there was no significant effect of strand length, specific pressure level, and the interaction between these factors on the moisture content value of BSB. Similarly, the analysis of variance found that there was no significant effect of strand length, specific pressure level, and the interaction of these factors on the density of tali BSP. However, the BSP complied the Japanese standard for particle board. The values of thickness swelling of the tali BSP fulfilled the requirements set forth by the Japanese standard 5908-2015. The highest and lowest TS values were found in BSP press at 30 kg per square centimeters. The analysis of variance revealed that specific pressure had a significant impact on the thickness swelling of tali BSP. The water absorption value of tali BSP ranged from 23.3 to 33.3. Analysis of variance revealed that strand length had a significant influence on the water absorption, whereas the specific pressure level had a highly significant influence on this property. It was found that the width expansion of tali BSP varied between 1.64% and 2.04%. The variance analysis revealed that the effect of strand length on the width expansion of tali BSP was highly significant, while the effects of pressure level and the interaction of strand length and pressure level were statistically not significant. The result of mechanical properties of tali bamboo strand board are presented in the slide. The highest internal bond strength of tali BSP was recorded for strand board prepared from 150 mm strand and pressed at 30 kg per square centimeter. The ANOVA revealed that there were significant effects of strand length, specific pressure, and the interaction of two factors on the IB of tali BSP. It could be observed from this figure that the screw holding power value for tali BSP pressed at 30 kg per square centimeter were higher than those of pressed at 25 kg per square centimeter. This finding was also supported by the analysis of variance result that revealed a significant effect of specific pressure and screw holding power. The BSP manufactured from 150 mm strand and priced at 30 kg per square centimeter generated the highest MOR value. The ANOVA showed that while the strand length had insignificant impact on MOR value, the specific pressure and the interaction between two factors significantly affected the MOR value. The average of modulus elasticity for the test specimens are shown in this figure. The MOE values for BSP pressed at 25 kg per square centimeter generally increase with increasing strand length, and the analysis of variance show that the effect of specific pressure and the interaction between strand length and specific pressure were highly significant. Finally, it can be concluded that strand dimension and specific pressure were found to have a significant effect toward physical and mechanical properties of tali BSP. The interaction of both factors were far more prominently affected the mechanical properties compared to the physical properties. The optimum condition to produce tali BSP by using strand length of 150 mm and specific pressure of 30 kg per square centimeter. And all properties of tali BSP in this research were able to meet the standard of Japanese A5908-2015 for particle boards type 24 to 10. We would like to acknowledge the Center for Standardization of Sustainable Forest Management Instruments, Ministry of Environment and Forestry, for supporting and facilitating the study. That, ladies and gentlemen, was what I wanted to share with you. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Hello everyone. Thanks for the time given to me. I will present the result of our research with the title Improving Dimensional Stability of Mahogany, Swietenia mahogany, wood with Oleracea of Dipterocarpus sp as a biocoating. The use of wood as a structural and non-structural material has been widely recognized. As a structural material, would prefer for its convenient and simple properties when used in the work process. In addition, wood is also a renewable resource. Mahogany wood is a type of hardwood that is widely used in the construction of furniture industry. In addition, mahogany has disadvantage, natural endurance, solidity, dimensional stability, and strength are relatively poor. Method to reduce distortion in wood dimension by applying treatments such as impregnation or compregnation on wood to replace some or even all of the water teeth to its cell walls. So, that the purpose of our study first, knowing the ability of oleoresin mixture as mahogany coatings, and second, seeing the discoloration that occurs. Samples were obtained from local sawmills with air dry condition. The type of wood used mahogany with the scientific name Swietenia mahagoni. This wood was obtained from a lumber shop in Samarinda. The observation used a quarter swan. The test sample was taken randomly from a sortiment with a size of 2 radial, 2 tangential, and 10 longitudinal centimeter. The coating liquids made of degrade oleoresin of the species Dipterocarpus gracilis, with a liquid concentration of 0%, 10%, 20%, and then 30% with diesel sulfurs. The coating was conducted with a brush and applied on air dry wood 3 times. The viscosity of the wood liquid was measured using Zen cup tool. Then the shrinkage swelling test followed the ASTM D14394 produced. Shrinkage was measured air dry to kiln dry. Discoloration of wood sample that are coated with oleoresin was carried out using a computer analyzed method to obtain the values of L, E, and B. Viscosity was performed to examine particle consistency and flow rate in each treatment. The viscosity result in figure show that the high viscosity occurred in the addition of oleoresin with a concentration of 30%, which is 230.71 CST, and the lowest viscosity was found with diesel fuel added, which is 5.60 CST. The concentration level of diesel fuel or oleoresin in wood sample has an effect on viscosity. The higher viscosity value of a product will be predicted to be thinner in outcome, which make it more difficult to coat. If the dispersed phase separation rate is lower, then the wood will be more stable in its dimension. The figure which show the wood weight was increasing with additional oleoresin. Wood weight increase in oleoresin concentration added about 1.16%, 1.60%, and then 2.11% with 10, 20, and 30 oleoresin. Wood was coated with oleoresin filling of lumen structure so that it could reduce the rate of water absorption and wettability. Meanwhile, 0.94% of weight increase with additional diesel fuel occurred due to boiling point of diesel fuel is between 250 degrees, to 200 degree, so there will be diesel fuel deposit in wood. This figure show the swelling and shrinkage value per treatment. Wood coating treatment with diesel fuel addition show 2.26 and 1.80 in the longitudinal direction, and then 4.53 and 3.26 in radial direction, and 8.95 and 6.33 in tangential direction. This value indicate that wood swelling and shrinkage in the longitudinal direction are lower than in both radial and tangential direction. The study is also indicate that wood coat with some older resin added show and increase dimensional stability. The figure can be seen the color characteristic of dimensional stabilization based on digital analysis. It can be seen that L has a range 0 to 100. The lower value of L show darker object or had no light reflection. A and B values have both positive and negative value. The lower value of A means that the object tends to be red, and the lower thing tends to be yellow. The addition of concentration of value of diesel fuel and other resin will be affect to wood color. Conclusion. High resin viscosity value indicate a higher concentration of wood product. In addition, viscosity increase along with the increase in wood weight and wood stability. Wood coat with resin show a darker color. Wood coat with various concentration of resin show increased dimensional stability in different directions. The degree of swelling and shrinkage of wood in the longitudinal direction is lower than in the direction of other wood cut. With resin coating, it shows that mahogany wood is stable in dimension. I think that's all that I can present to you. Thank you for attention.
Okay, Mr. Jamaluddin.
Yeah.
I
think one left.
Yeah.
Or no?
Yeah, the last presenter may be live.
Yeah. Okay. Yes, please.
Mr. Budi Sasono has already joined us with us. Okay. About 10 minutes, time is yours.
Halo, Pak Budi.
Pak Budi is still mute. I'm sorry.
Unmute. Okay. It is clear?
Yeah.
Thank you. Thank you very much for the time. I'm sorry I could not open the video due to the internet connection. In this present, I will speak about the one-step purification and characterization of glucosidase enzyme from Panay Bacillus polymixa. As introduction, beta-glucosidase are a class of enzymes that catalyze the hydrolysis of beta-1,4 glycoside linkage that will be releasing non-reducing terminal glucosyl residues from glucosidase and also oligosaccharides. The enzyme, together with the L-arabinose isomerase, can produce D-tagatose from lactose. As you know, that D-tagatose has function as anti-diabetics or drug-like sweetener. Moreover, the enzyme also has ability to perform transglycosylation to produce galacto-oligosaccharides. Galacto-oligosaccharides now almost is used as a prebiotic, especially to increase the absorbance of calcium in the body. So it is a useful compound, especially for the old people to protect their bone. Due to the importance of the enzyme, we then synthesize the enzyme. Synthesize the enzyme through molecular cloning and express the enzyme in E. coli PL21DE3. Our preliminary data show that the crude enzyme can hydrolyze the lactose into galactose and glucose, and at the same time also produce galacto-oligosaccharides through transglycosylation reaction. So, due to the interested result, we then trying to purify and characterize the enzyme. Firstly, we produce the enzyme using a standard procedure. The E. coli BL21DE3 harboring plasmid Bigel B was cultured overnight at 37 degrees Celsius with shaking. Then overnight culture was inoculated at fresh LB media, and then was cultured at the same condition until the OD 600 nanometer value reached 0.5. Cells were induced with 1 millimolar isopropyl beta D-thiogalactopyranosate or IPTG, and again culture for 16 hours with the same condition. In this culture then were collected by centrifugation, suspended at buffer postbed, and disrupted using sonication. The lysate were centrifugated, and the supernatant obtained was further purified by His-Tech affinity chromatography. Beta-glucosidase was elute using buffer B contained 250 millimolar imidazole. The purified was verified by the presence of the single bond on STS page electrophoresis. Enzyme activity was determined using 5 millimolar paranitrophenyl beta D-glucopyranosate or PNPG as a substrate. The reaction was stopped by adding 1% of sodium carbonate, and the absorbance was measured at 400 nanometer. 1 unit of beta-glucosidase activity was defined as the amount of enzyme that produce 1 micromole of paranitrophenol per minute. As a result, the enzyme was expressed as soluble form here with molecular weight of 52.5 kilodalton. SDS-based electrophoresis shown that there is a single band with molecular weight of 52.5 kilodalton at eluate fraction. The activity of the pure enzyme was 4.1 unit per milligram, increased 2.2-fold compared to those of the crude enzyme. Thus, the enzyme was purified with a single-step purification using high-tech column chromatography. Then we continue to the characterization of the enzyme. The enzyme activity was evaluated at various temperature from 30 degrees Celsius to 70 degrees Celsius, and also at various pH from pH 5.0 to 9.0, like shown in the graph. The pure enzyme has optimum temperature at 50 to 50 degrees Celsius. The enzyme activity decreased significantly when the temperature was below 50 degrees Celsius or above 55 degrees Celsius. The enzyme activity exhibit optimum pH at 6.0 and remain high activity at pH 7.0. The pure enzyme exhibit higher activity in phosphate buffer compared to those in trace buffer under the same pH condition. And for ion dependent, the residual activity of metal free enzyme was assessed by incubating with 1 millimolar metal ion for 10 minutes. As shown in the table, only metal zinc ion has strong inhibition on the enzyme activity. To summarize, the pure enzyme possesses a good environmental condition, including temperature, pH value, and metal ions. This result provides an important reference for the selection of the appropriate fermentation condition for ditegatose production and also galacto-oligosaccharide production. As a conclusion, in this study, recombinant beta-glucosidase from Paenibacillus polymixa was purified and characterized. The result shown that the pure enzyme has specific activity up to 4.1 unit per milligram, optimum temperature and pH at 55 degree and 6.0 respectively. The pure enzyme was inhibited strongly by addition of 1 millimolar metal zinc ion. The results suggest that beta-glucosidase from Panayobacillus polymixa has potential properties to be used in D-tagatos production. Thank you very much.
Okay, thank you, Budi.
Yeah, you're welcome.
And all participants. So we can move to the Q&A session. So if participants have any question, please deliver to whom. You can mention the presenter. Any question, please?
Any question? Maybe Prof. Aris? Do you have any question?
Prof. Aris will.
Data to data.
Oh,
I don't have it.
Mbak Deta, raise hand.
Okay.
This data.
Yes, please.
Okay, thank you, Mr. I have a question for Ms. Shamshidar. Can you explain again? Because I seen that the figure 5, there is a bioplastic, and I still don't get it. This bioplastic that already composite with cellulose or not yet composite. And then the second question for Miss Aulia. According to the conclusion, I seen that the coating with oleoresin show darker color, isn't it? And could you explain it why? And how about the stability and lifetime using that bio coating? Thank you.
Okay, thank you, Ms. Ayu. And any other question? Not Ms. Yunis Musnar, you can answer first the question from Ayu, please. Halo, Bu Yusnidar.
Yes, thank you. Could you
Yes,
repeat again the question?
Oh. Sayo, can you please repeat your question?
Okay, Miss. When I see your presentation, there is a figure 5, isn't it? And in that figure, I still don't get it. The figure is bioplastic already composite with cellulose or not yet? And you could explain it, the differences between A, B, and C, and the correlating with the cellulose itself. Thank you.
The figure, this is the burial of bioplastic. The A is 0, and B is a week, and the C is 2 weeks, and the D is 3 weeks.
Oh, so it means the bioplastic is already composite with cellulose, isn't it?
Yes, this is a composite of bioplastic
and then
from the rice husk.
Oh, rice husk. You using 3 kind of treatment, Miss, the autoclave, and then maceration, and what?
Oh yes,
microwave.
Not 3. The pre-treatment. This is just only the maceration.
Oh,
because I get the high cellulose among cellulose.
Oh, okay. Thank you.
Thank you, Ms. Arya.
Okay, thank you, Samsidar. Any others question?
Mr. Jamaluddin, question to Mr. Aulia.
Oh, yeah, please.
Okay, thank you. Thank you, Miss Benedita. About this discoloration, the discoloration is some concentration indicate that the addition of concentration will affect the color of darker wood. A low L value indicate that the object is darker or has no reflect light. And then meanwhile, a low A value means that the object tends to be red. And then the low B object tends to be yellow. For second question, maybe our research does not cover that. I have not been able to provide an answer. Maybe this can be an input for us for future research. Thank you.
Okay, thank you, Miss Aulia.
Thank you, Miss.
Okay, thank you, Aulia. I have question for Bu Sanidar. As far as I know that rice husk is contain very high silica, right? So is that does it affect to tensile strength or longevity of the bioplastic? Hello?
Hello.
Yes, please.
Yes. From the code table, the mechanical property of rice husk bioplastic, we compare the microwave and maceration and autoclave, the tensile strength from the three pretreatment. The higher is in the we using microwave, and the elongation, the higher in we using autoclave.
So you mean the silica has been removed? Is it?
There isn't silica.
The silica has been
there isn't silica in my research.
Okay.
I make the rice husk from bioplastic, not silica.
Oh, okay. Never mind. Okay, any other question from our participant?
From Mr. Jamaluddin,
yeah.
Maybe we have 3 minutes again.
Yeah.
But I have a question to the other the presenter. Okay.
Yes, please. One only.
Yeah. To Mr. Jahidin or Miss Yuka Milan. Hello.
Hello.
Okay, my question is there any pretreatment or pretreatment opportunities so that pyrolysis can be suppressed at lower temperatures? And then question to Mrs. Desi, is there an opportunity to use a mixture of bamboo and wood so that strand board will appear which has improved properties? Last but not least, my question to Mr. Budi, is this a specific enzyme produced by fine ligacillus polymexa? Thank you.
Okay, can you repeat again your question?
Who is this?
For presenter.
Oh, Mr. Jaiding. Oh, yeah. So, Mr. Jaiding or Miss Yuka Milan, is there any pretreatment or pretreatment opportunities so that pyrolysis in your research can be suppressed at lower temperatures?
Oh, got it, Jaiding?
I'm sorry. Okay.
Is there any option to make temperature lower like that? Yes.
Yes.
Yeah.
Yes. Maybe like we can conduct a pre-treatment.
Yeah. Can you make a lower temperature for pyrolysis process? It's hiding. How much you want, Pak Adik?
Yes, okay, it's okay. Maybe okay. Next time we will take contact again. So my question to Miss Desi: is there an opportunity to use mixture of bamboo and wood, so that strand board will appear which has improved properties?
Halo, Bu Desi.
Yeah. Yes. Can you hear my voice?
Yes, clearly.
Yes.
Okay.
Yeah. Sorry, I couldn't clearly hear your question, but I only hear that is there any opportunity to mix bamboo and wood to make the strand board? Is it? Yeah.
Yes.
So that was the question, and the answer is yes, because there are many research about hybrid bamboo and wood strand board, and it also gives excellent physical and mechanical properties. And I also write it on the full paper of our research. But the next question, I'm sorry, I couldn't get it. Could you please repeat it again?
No. My question is enough. Just one.
Only one.
Thank you very much. Very clear.
Please already answer your question. Thank you.
Thank you. To Mr.
Okay,
Budi.
thank you, Pak Adik. Is there anything else?
Last but least to Mr. Budi.
Yes. Thank you for the question. Maybe I want to make it clear that you asked about whether the enzyme is specifically from Bacillus polymexa. Is it?
Yes, specific enzyme produced by Bacillus polymexa.
Oh, yeah. Actually, beta-glucosidase can be produced from many microbial bacteria and also fungi. So the important thing is that the character of the enzyme. We already produce other enzyme like L-arabinose isomerase with properties such as optimum pH 5.5 and temperature is 55 degrees Celsius. So when I need to produce the enzyme beta-glucosidase with similar properties with L-arabinose isomerase, then we searching from papers, we compare with other microbes, and we find out that the beta-glucosidase from Bacillus polymixa has the target properties. So then we cloning the gene from Bacillus polymixa. It is okay?
Okay, thank you. Really.
You're welcome.
Okay, the time is up.
Time is up.
Adik, yeah.
Thank you very much.
So I think that's enough. And thank you again for all presentation and also for attending this room in term of the electrolysis processing of the electrolysis. We can joining to back to the main room.
Okay. Thank you, Pak Jamal.
Yes. Please, Nujul.
Okay, thank you. Thank you very much for Chair Pak Jamaluddin Malik and Co-Chair Pak Adik Bahanawan and all distinguished participants. I think this session is over and we can go back to the main room for the closing ceremony and announcement of best paper and best presenter. Okay, I think we can directly go to the main room. Thank you.
Recording stopped. Recording in progress.
Sekarang yang terjadi